Hello children, Physics Plaza welcomes you all to the Maha Marathon of Class 10 Physics ICSE. The final day has come children, we have to complete the revision of all chapters. Just be ready with your notebook and pen children, believe in you, believe in us. We will promise you that we will be taking you all through the best revision for today's class. And we promise you that at the end of this session, you will be very comfortable and you will be very confident to face your board exams. So definitely children, definitely what I mean to say that after listening this class children, yes, you get a confidence and definitely you will win the battle of your exam. Okay, chalo, all the best for you, all the best for all of us also. So without doing delay, we will be starting today's class. 3, 2, 1, go. Yes, the first chapter is force children. Children, what is a force? It is an external cause which tends to change the shape of an object, size of an object, position of an object, direction of object also. According to the Newton's second law of motion, F is equal to ma, and force is a vector quantity. Its SI units are Newton, CJ units are dyne. Okay, and how these two are related? 1 Newton is equal to 10 power 5 dyne. And children, here one important relation is that here 1 kgf is equal to 9.8 Newton. Now what happens when force acts on a body? So it depends. Here we have to see whether a body is free to move or it is pivoted. If a body is free to move, the body will show translational motion. If a body is pivoted, it will show rotational motion. Next come to the movement of a force. Children, whenever a body is pivoted, example like a door, when a force is applied on it, what will happen? There will be a turning effect. So, turning effect on a body about a axis of rotation is only due to the movement of force, so called torque. So, mathematically how can we define? Moment of force is defined as the product of magnitude of force and perpendicular distance between point of application of force to the axis of rotation. So mathematically tau is equal to F into R, and moment of force, like force, torque is a vector quantity. Its SI units are Newton meter, CJ units are dyne centimeter here. Now how these two are related children? 1 Newton meter is equal to 10 power 5 dyne centimeter. And in exam they may ask a question, how can you increase the moment of force? Yes, by increasing the magnitude of the force or by increasing the perpendicular distance. Even with the help of both also we can increase. Then how can we decrease the moment of force? By decreasing the magnitude of force and perpendicular distance, we can decrease the torque. Fine? Yes. And here one more important thing children. So clockwise moment of force is taken as a negative, anti-clockwise moment of force is taken as a positive. And what are the examples children? So if you want to understand the example, so you should let us recall once again. Tau is equal to F into R children. Can we write like this? F is equal to tau by R? Yes. For a given moment of force, force is inversely proportional to the perpendicular distance. Which means what? If you increase the perpendicular distance, definitely magnitude of the force, whatever the magnitude of force which is required will be less. Means if perpendicular distance is more, effort required will be very less. Is it clear? So because of that only, spanner is provided with a long handle. Why? So spanner with a long handle, perpendicular distance is more, so that less effort is required to produce the enough moment of force. So same thing happens with door. Why a handle is provided at the end of the door only? At the end of the door, because perpendicular distance is more, so that less effort is required to open the door, to close the door. Same thing with the screw jack also, or jack screw. Is it clear? Fine children. Next, couple. What is a couple? Hey, generally when we go to the marriage, we can see that, hey, see the couple, it's made for each other, right? Okay, actually couple means what children? Two. But here we are talking about not a bride or a bridegroom. Here we will be talking about the two forces children. So what is a couple here? Two equal anti-parallel forces but not acting along the same line of action of force form couple. Is it clear? Fine children. And here you can see here two equal forces acting on the same body which is pivoted in a opposite direction. Both are parallel only but opposite direction. Example children, if you want to turn the tap, yes, there couple is needed. And even children, if you want to open the bottle cap, close the bottle cap, and even what we can say, turning of a key in a lock, these all are the examples of couple which are related to our day-to-day life. Okay, fine. Next, movement of a couple. So how to define the movement of a couple? It is a product of either a force and perpendicular distance between these two forces, that is F into D. So movement of a couple is also vector only, and its units, torque units, both are same. Done? Yes. Now come to the equilibrium. Now it's come to the equilibrium. What is the equilibrium, children? Several forces acting on a body do not change either the state of rest or state of uniform motion. Then the body is said to be in equilibrium. Here we have two types of equilibrium, children. Static equilibrium, dynamic equilibrium. What is the static equilibrium? Number of forces acting on a body, what we can say, they do not change its state of rest. Then we can say that body is in static equilibrium. Example, the book lying on the table. Yes, even beam balance in equilibrium. If you can see the beam of the beam balance, children, when you are measuring, so both pans will be in a, in the same level. In that condition, the beam will be in a static equilibrium. When come to the dynamic equilibrium, what is a dynamic equilibrium, children? Here, the number of forces acting on a body do not change either its state of uniform motion or a state of what we can say circular motion. Then we can say that the body is in dynamic equilibrium. Example, children, the moon revolving around the earth. Yes, it comes under dynamic equilibrium. And here, the water drop which is falling with a uniform speed near the earth's surface. Yes, taken as example for dynamic equilibrium. Examination point of view, they will ask us to write the conditions. What is the first condition, children? Yes, the resultant of all the forces acting on a body must be 0. That is, algebraic sum of the forces acting on a body must be 0. Second one, the algebraic sum of the moments of force about a point of rotation must be 0. So writing this is mandatory. About point of rotation is 0. Yes. Next, principle of moments, children. What is the principle of moments? In equilibrium, the sum of clockwise moments of forces are always equal to the sum of the anti-clockwise moments of forces. In a single statement, we can say that in equilibrium, the algebraic sum of the moments of forces about the pivot point of rotation must be 0. And here, beam balance will work on this principle of moments. In exam, they may ask a question, name a device which works on this principle of moments. Yes, you have to write beam balance. Is it clear? Fine, children. Just copy this. We will discuss now about the center of gravity and circular motion. Hope have you copied this? Hope you have copied. Okay, now done. Yes. Okay, children. Now come to the center of gravity. Children, what is the center of gravity? The point about which the algebraic sum of the weights of all the particles constituting the body must be 0. Is that clear? Fine, children. And the important point regarding center of gravity is that it can be situated outside of its material also. So in exam, they may ask you a question, can the center of gravity be situated outside of its material? Yes, it can be. Example, what, children? It is the ring. And the center of gravity depends on shape of an object, mass distribution. By changing the shape of an object, children, the center of gravity will be shifted. For example, if you can take a thin wire, center of gravity will be at a midpoint. For suppose, one wire will be there like this, one wire will be there. Its center of gravity will be somewhere else here. If it is made in the form of a ring, what will happen? Center of gravity will be situated to this point. Is it clear? So that is how we can say that center of gravity depends on shape of an object. Okay, fine. And here, children, let us see a few examples of center of gravity of an object. Especially examination point of view, center of gravity of a solid cone, hollow cone is very important. So center of gravity of solid cone from its base is h by 4. Whereas center of gravity of hollow cone from its base it is h by 3. And the very important thing is that sometimes they will ask from a vertex. Vertex means what? This height they will ask. So to get this, what we have to do? H minus h by 3. So this is going to be 2h by 3 from its vertex. Whereas in the case of solid cone, it is going to be 3h by 4. Okay, for a triangular line, children, the point of intersection of medians, whereas for a square or a rectangle, the point of intersection of diagonals, whereas for a rod, at center rod will be at its midpoint. Clear? Done. Now come to the uniform linear motion. Children, what is a linear motion? If any object is going along a straight line path, such a motion is called linear motion. Uniform linear motion means what actually? A body is covering equal displacements in equal interval of timings. Then the body is said to be moving with a uniform motion. So the body which is in uniform motion, children, it has means its speed and velocity remains constant. As the velocity remains constant, children, definitely what will happen? Acceleration will be 0. As it is acceleration is 0, that's what uniform linear motion is also called as unaccelerated motion. Then come to the uniform circular motion. What is circular motion? If any object is going along a circular path, such a motion is a circular motion. But what is the uniform circular motion? In a circular motion, if a body has uniform speed, such a motion we can call it the uniform circular motion. Means in a uniform circular motion, children, speed remains constant but not velocity. Which means what here? Look at this diagram. This diagram is a very important examination point of view. So at every point, velocity magnitude might be same, but its direction is changing. Which means what? As velocity is a vector quantity, its velocity, its direction is changing. So velocity is a variable. As velocity is a variable, children, definitely acceleration is not 0. That is the reason why uniform circular motion is also called as accelerated motion. Clear? Fine, children. Now come to the centripetal force and the centrifugal force. Children, in exam they may ask a question. So name the force which is required to keep a body in a uniform circular motion or a circular motion. Yes, it is nothing but centripetal force. So centripetal force is needed for any object to go in a circular path. And the centripetal force is a real force. It is always towards the center. Why it is a real force? Yes, external cause will be there. That's what centripetal force is a real force. It is always towards the center of a circular path. You must write center of circular path. You must write. Examples, let us see, children. If you can take an electron nucleus system, the electrostatic force between electron and a nucleus provides centripetal force. Whereas a planet sun system, in that gravitational force provides centripetal force. If you can take a string and a stone system, a stone is attached to a string and go on whirling like this, then what happens? Their string provides, their tension force will be there. Okay, now that provides the required centripetal force. When comes to the centrifugal force, the force which is directed away from the center of circular path is called centrifugal force. It is not a real force, rather it is a fictitious force, children. When you can see the magnitudes of a centripetal and centrifugal forces, yes, both are equal. That's what we can write. The ratio of the magnitudes of centripetal and centrifugal force are 1:1. But why it is a minus here? Because both are equal in magnitude but opposite direction only. Children, because both are equal in opposite direction, can we say that centripetal and centrifugal forces both can form action-reaction forces? No, they can never form action-reaction pair. You may get a note, sir. Why not, sir? Both are equal and opposite. Should try to understand. Once recall reaction, what we can say, action-reaction pair. Action-reaction forces will act on two different bodies. But whereas here, centripetal and centrifugal, both forces are acting on the same body. Hence, they do not form action-reaction forces. So, this is the fourth chapter. Is it clear? Just copy the concepts. We will discuss the concepts of work, power, energy. Come to the work, power, and energy. First, we see what is work. Children, this work is a common term which will come across with this word in every day, but scientifically work is different, I can say that. So children, what is work done? When the work is said to be done? Children, work is said to be done only when the force applied on a body makes a body to get some displaced. Okay, in that case only we can say that work is said to be done. So work is a scalar quantity. Mathematically, work is equal to product of, work is defined as the product of force and displacement. Its SI units are Newton meter, it is also called as joule. Its CGS units are dyne centimeter, it is also called as erg. Children, 1 joule is equal to 10 power 7 erg, or 1 erg is equal to 10 power minus 7 joule. Children, it is not compulsory that always a body should be displaced in the direction of applied force. In some cases, so force means body may not be displaced in the direction of applied force. In that case, how to calculate? Yes, children, in that case, we can calculate here W is equal to Fs cos theta. What is the theta here? Theta is the angle between force and displacement. Children, based on this only, now we can understand the positive work done, negative work done, and zero work done. When the work done can be positive. Children, if a body is displaced in the direction of applied force, then work done is said to be positive. In that case, so angle between both are parallel means what? Angle between force and displacement is 0. So cos 0, theta is equal to 0 degrees. Cos 0 is 1. So F into S into 1 is 1. So W is positive. Example, the work done by the body is falling freely. So on this body, gravitational force will be acting in which direction? Downward direction. So the work done by the gravitational force on the freely falling body is always positive. Clear? Fine. Now children, if a body is displaced opposite to the direction of applied force, which means what here? For example, here body is moving in this direction and force is acting in this direction. Then what happens? That angle will be 180 degrees. Cos 180 is minus 1. So Fs into minus 1 will be minus 1, minus Fs. So work done is negative. Example children, now a ball is going vertical upward direction, but gravitational force will be acting downward direction. So force is downward, body displacement is upward. So in this case, the work done by the gravitational force on the body moving vertically upward direction is negative. And children, during the cricket match, a fielder is trying to catch a ball. In that case, work done by the fielder is a negative. This is a very important examination point of view. And in exam, they might ask a question, what are the cases where work done can be 0? If no force is acting, work done can be 0. Force is acting, but displacement is 0. Which case it is possible? Yes. Try to push the wall, children. You will be applying the force, but you cannot make the wall to move, right? Displacement is 0, work done can be 0. But third case very important. Force is acting, body is displaced. Still, work done will be 0. In that case, force must be perpendicular to the displacement. In that case, theta is equal to 90 degrees. Cos 90, 0. Fs into 0 will be 0. So, let me give you one application here. For example, children, here is satellite moving around the earth. In this case, the force will be towards the center, centripetal force. But displacement will be always along the tangent. So, this angle will be 90 degrees. That's what in this case. So, what is the work done on the moving, what we can say moon which is revolving around the earth is 0 only. Because the angle between the force and displacement at every point is 90 degrees only. Clear? Fine children. Now come to the, and how can you measure the work done by the gravitational force? For example, whenever you are lifting a body, you are lifting the body against the gravitational force. In that case, how can we measure the work done, children? mgh. To what height you are measuring, to what height you are lifting, and what is the mass of the body, and g value. So mgh is our expression to calculate the work done by the gravitational force. Come to the power, children. What is the power? The rate of doing work is called power. Children, work depends on magnitude of force and the displacement. Whereas here, power depends on work and time. It's a SI units are joule per second. It is also called as watt. It can be, even you can measure kilowatt, megawatt, gigawatt also. CJ units are erg per second. How this SI unit, CJ unit are related, children? 1 joule per second is equal to 10 power 7 erg per second. It's a very important. And power also can be defined as a dot product of force and velocity or speed, we can say that. Is it clear? Fine children. So as I told you that power depends on two factors, work and time. Power is proportional to the work done but inversely proportional to time, which means what? If a same work is done, then we have to the time. The person who can do the work in a less time is said to be having more power. So based on this, we can expect some numericals also. Clear? Fine children. And here, so especially whenever we are measuring power in terms of mechanical engineering, this common unit which we can use. What is that? Horsepower. 1 horsepower is equal to 746 watts or 1 kilowatt is equal to 1.34 horsepower. Children, examination, they might ask the difference between work and power. How can you write? First write the definitions. Okay, now work definition, power definition. Work does not depend on time, power depends on time. The SI unit of work is a what we can say joule, whereas the SI unit of power is watt. Clear? Yes. Come to the energy. What is the energy? The ability to do the work. If you have more energy, you can perform more work. If you have less energy, you can perform less work. Its SI unit is like work is a joule and the CGS unit is erg. As we know that 1 joule is equal to 10 power 7 erg. And we know that energy can be of different forms. If you want to measure the heat energy, there mostly will be using a calorie, right? So 1 calorie is equal to 4.2 joules or 1 joule is equal to 0.24 calories. And electron volt is a unit, it is a unit to measure the energy of subatomic particles. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. And watt hour, kilowatt hour. So these units are used to measure the electrical energy. 1 watt hour is equal to 3600 joules, whereas 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. Clear? Fine. Now comes to the mechanical energy. What is the mechanical energy, children? The energy possessed by an object by virtue of its state of rest or state of motion is called mechanical energy. And the mechanical energy is of two types: potential energy, kinetic energy. What is the potential energy, children? The energy possessed by an object by virtue of its state of position or a configuration is called potential energy. Potential energy is of two types: gravitational potential energy, elastic potential energy. Children, whenever you are lifting objects against gravity, some work is done. That work done is stored in the form of potential energy, so-called gravitational potential energy, which can be measured by mgh formulae. Children, at infinity, gravitational potential energy is zero. It's very important. And second one is elastic potential energy. Children, whenever a body is deformed, so during that process, what will happen? There will be change in the configuration. So due to that, so the body will gain some energy, right? So the energy gain due to the deformation, what we can state of deform, we can call it as a elastic potential energy. Comes to the kinetic energy, children. What is the kinetic energy? The energy possessed by an object by virtue of its state of motion is called kinetic energy. It is of three types: translational kinetic energy, vibrational kinetic energy, rotational kinetic energy. Now we will see the relation between kinetic energy and the linear momentum. At the same time, we see the work energy theorem and the different forms of energy and the law of conservation of energy. Hope it is copied, children. Just copy this. Root TGH. Fine, children. So let us come to the kinetic energy. We know that the energy possessed by a body by virtue of its motion is called kinetic energy. Then what is the linear momentum? The product of mass and velocity is called what, children? Linear momentum. And yet the relation between these two is kinetic energy is called p square by 2m, or p is equal to square root of 2m into kinetic energy. Here we have three important cases, children, very important. If linear momentum remains constant, then kinetic energy is inversely proportional to the mass, which means what? In this case, children, here lighter body will have more kinetic energy, heavier body will have less kinetic energy. But whereas if the velocity of the two bodies is same, that is v is a constant, then kinetic energy is proportional to mass, which means what? Here heavier body will have more kinetic energy, lighter body will have less kinetic energy. In this case only, if both bodies will have same kinetic energy, then linear momentum is proportional to the square root of mass, which means what? More the mass, more the linear momentum, which means what? Here according to this, heavier body will have more momentum than lighter body. Now comes to the work energy theorem. Let us say initially a body is moving with a velocity u, then force is acting on the body in the direction of motion. Obviously its velocity increases, simultaneously some work is done. This work done only is equal to the change in its kinetic energy. So in exam they may ask you a question: state the work energy theorem. The work done on the body, work done on the moving body in the direction of motion is always equal to the change in its kinetic energy, or simply increase in its kinetic energy. If a force will act in the opposite direction, decrease in its kinetic energy. In exam they may ask a mathematical form of work energy theorem. So W is equal to half mv square minus half mu square. Now comes the conversions of energy. Children, in our daily life we know very well, so how the energy conversion will takes place. For suppose in the loudspeaker, what happened? Electrical energy is converted into what we can just sound energy. whereas microphone, sound energy is converted into electrical energy. Photosynthesis, light energy is converted into chemical energy. In a bulb, electrical energy is converted into light, mostly light only, but heat. Heater, water heater will be there. Electrical energy is converted into heat energy. And the cell in a use, yes, when the cell is in use, chemical energy is converted into electrical energy. If a cell is charging, in that case, what children, electrical energy is converted into chemical energy. Now come to the law of conservation of energy. Children, what is the law of conservation of energy? According to law of conservation of energy, energy can neither be created nor be destroyed, but it can be transferred from one form to another form. Children, if there is only energy exchange between potential to kinetic, kinetic to potential, then mechanical energy always remains constant, provided there is no heat loss to the there is no energy loss to the surroundings. So the sum of the kinetic and potential energy always remains constant, provided what, children? So there is no heat loss means what? It only happens if there is no air friction. In the absence of air friction only, the sum of the kinetic and potential energies always remains constant, which means what? Mechanical energy remains constant. In exam, they may ask a question. Give any two examples where mechanical energy remains constant. Two examples: freely falling body. Second one is simple pendulum. Children, in the case of freely falling body, just imagine that a body of mass is dropped from a height of h. Then, children, at its initial position, it doesn't have any velocity, which means what? At a point A, it has only mgh, means the mechanical energy is only due to the potential energy, kinetic energy is 0. But at a point C, just it is about to hit the ground, it has only kinetic energy, means mechanical energy only in the form of kinetic energy, and its potential energy is 0. Exactly half of its height I am talking, half of its height, what happens? Mechanical energy or potential energy is equal to the kinetic energy, which is equal to the mgh by 2. Now come to the simple pendulum, children. It's an oscillating simple pendulum. At extreme positions, it has only potential energy. At a mean position, I mean while it is crossing the mean position, it has only kinetic energy. So then how to find, children? In exam they may ask a question. In order to raise a height of h, what should be the velocity given here? Then according to law of conservation of energy, energy at a point A must be equal to energy at a point C or B. Anything is okay. So EA is equal to EB. At EA only kinetic energy, at B it has a potential energy. Just simple mass will get cancelled, and V is equal to square root of 2gh. Sometimes if a velocity V is given, to what height it is raised, then children, h is equal to V square by 2g. This formula we can use. And here in the case of freely falling body, children, in these two cases, especially in this case, they might ask, it's draw a graph which gives the relation between energy to the height, children. So it's very important. Look at here. So let us suppose it is a height, let us the mechanical energy. As height increase, what will happen? Potential energy increase. So this graph indicates potential energy. Whereas when height is increases, simultaneously kinetic energy keeps on decreasing. So this graph shows kinetic energy. This exactly what, children? Half of its height. Exactly at half of its height, PE is equal to mgh by 2 only, KE is equal to mgh by 2 only. But whereas here the total mechanical energy remains constant. This is mgh. Okay, children. So these are the concepts of work, power, energy. Children, now we see the concepts of machine, children. First of all, what is a machine? It is a device which makes our work easy and comfortable. Means so much of work is done with a less efforts in a less time. What are the functions of machine, children? Machine acts like a force multiplier, machine acts like a speed multiplier, and machine can change the direction of effort applied, and it also can change the point of application of effort to the convenient point. And here some terms are very important examination point of view. What is that? Mechanical advantage. It is the ratio between load and effort. Next, velocity ratio. Actually, it's very important. So in exam they may ask a question. Name the term which remains constant for a given for a machine of a given device design. That is a velocity ratio. It is defined as the, children, better you can take this definition. So it's ratio of effort velocity to the load velocity. And what is the efficiency, children? The ratio of work output to the work input. These three do not have a units because these three are ratio of same two physical quantities. And these three, how they are related is very important. Efficiency is equal to mechanical advantage by velocity ratio. It also can be written as mechanical advantage is equal to efficiency into velocity ratio. Children, machines are of two types. Ideal machines will be there, actual machines are there. So ideal machines, of course, practical it is not possible. So actual machine or practical machine it is. So the machine which we are using daily life. So in exam they may ask you to write the differences. So for ideal machine, children, work output is always equal to work input. Whereas for actual machine or a practical machine, work output is less than work input. Here mechanical advantage is equal to velocity ratio, efficiency is equal to 1 or 100%. Here mechanical advantage is less than velocity ratio and efficiency is less than 1 or less than 100%. And here they might ask a question, why for actual machine efficiency is always less than 1? Why it can't be 100%? Because of three reasons, children. What is the first reason? Because of presence of friction. Second one, because of weights of parts of the machine. Third one, what are the strings which are used? They may not be a pure elastic in nature. Okay, na? So these are the reason why a machine cannot be 100% efficient. Okay, fine. Now comes to the lever, children. On which principle does it? What is a lever, children? Here it is a rigid, straight or bent bar which is able to rotate about a fulcrum or about a point, a pivot point, we can say that. Okay, and which principle does it work? It works on principle of moments. That is what? In equilibrium, the sum of anti-clockwise moments are always equal to the sum of clockwise moments. Clear? Fine, children. And the mechanical advantage of lever is effort arm by load arm. What is the effort arm, children? The distance between fulcrum to the effort is called effort arm. What is the load arm? The distance between fulcrum to the load is called load arm. So based on the relative positions of effort, load, what we can say fulcrum, levers are classified into three categories. First we see the class 1 lever, and before that, children, it's very important. If a effort arm is greater than the load arm, then mechanical advantage is greater than 1, it acts like a force multiplier. If a effort arm is less than load arm, its mechanical advantage will be less than 1, it acts like a what we can say speed multiplier. If effort arm is equal to load arm, the mechanical advantage can be equal to 1. So there it is used to change the direction of effort applied. Okay, now fine. Class 1 lever. So what is the class 1 lever, children? So for a class 1 lever, fulcrum will be in middle and on either of sides load and effort can be. And the very important thing, children, as fulcrum is in between and it is movable, so you can move this towards effort or you can move towards load, which means what? You can adjust load arm and you can adjust effort arm. So based on that, so effort arm can be greater than load arm, so mechanical advantage can be greater than 1. So which means what? Class 1 lever can act like a force multipliers. Example what, children? Crowbar, we can say that. Crowbar, okay, and the shears will be there which we use to cut the plants, and a metallic cutter will be there, it comes under class 1 lever which acts like a force multiplier. And here, children, for suppose if this fulcrum is taken towards the effort, then what will happen? Effort arm will be less than that of the load arm. In that case, mechanical advantage will be less than 1. So example, what is scissors which we use to cut the cloth, right? So which acts like a speed multiplier. And if it is middle exactly, then effort arm is equal to load arm. In that case, mechanical advantage is equal to 1. So seesaw case. So which means what, children? Here class 1 levers are all rounders. They can act like a force multiplier, they can act like a speed multiplier, they also can it is to change the direction of effort applied. But children, can we use same machine simultaneously force multiplier and a speed multiplier? No, we can't use either force multiplier or speed multiplier. And it comes to the class 2 lever. In a class 2 lever, load will be in middle and either of sides fulcrum and effort will be there. So if you can see, children, for a class 2 levers, effort arm is always greater than load arm, which means what? Mechanical advantage of class 2 lever is always greater than 1. So that class 2 levers always acts like a force multipliers. Bahubalis, class 2 levers always force multipliers. Example, nutcracker, lemon squeezer. Okay, fine. Comes the third class 3 levers. In the class 3 levers, effort will be in middle and fulcrum and load are either of side. If you can notice the class 3 levers, children, here, load arm is always less than effort arm or effort arm is always less than load arm. So as effort arm is always less than load arm, mechanical advantage is less than 1. So what we can say, class 3 levers always acts as a speed multipliers. So this is about actually the terms related and the class 1, class 2, class 3. Now we see the pulleys, like what is the pulley, types of pulley, and a combination of pulley and a block and tackle system. Here is load, so load direction will be always downward direction. Children, here yes comes to the single fixed pulley. Children, what is single fixed pulley? Children, the pulley whose axis of rotation is fixed, which is not movable. So look at it, so it is a fixed to this only. And the very important thing is that what is the mechanical advantage, what is the velocity ratio, and what is its use, that we need to understand. Children, if you can see here, effort is balanced by tension. So here load also balanced by tension. So here mechanical advantage is equal to, we know, load by effort. So this is T by T, both will get cancelled. So it is 1. So mechanical advantage of single fixed pulley is 1. What about velocity ratio, children? Here the very important thing is that effort displacement is always equal to load displacement, which means what? Velocity ratio also 1. So efficiency is equal to 1. Children, as mechanical advantage and velocity ratio is equal to 1, so hence a single fixed pulley is used to change the direction of effort applied. Now come to the single movable pulley. What is a single movable pulley? The single pulley whose axis of rotation is movable is called single movable pulley. And what is its mechanical advantage? If you can see, children, here its mechanical advantage. So here effort is balanced by tension and the load is balanced by two segments of the string. Hence mechanical advantage is equal to load by effort, that is 2T by T. T cancel, it is a 2. And the velocity ratio, children, what is the velocity? Very important. Velocity ratio of single movable pulley is that effort displacement by load displacement. Children, here effort displacement is equal to load displacement, but it is very important thing is that effort displacement of single movable pulley is always double than that of the single fixed pulley. Sorry, try to understand. Excuse me. In a single movable pulley, children, the effort displacement is always double than that of the load displacement. For example, if load is displaced by x, then effort is displaced by 2x. X cancel. So velocity ratio of the single movable pulley is 2. And here obviously efficiency is equal to 1 only, that is 100%. So for a single movable pulley, mechanical advantage and velocity ratio is equal to, which means what? Greater than 1. Hence single movable pulley acts like a force multipliers. Okay, but one problem is there. Though single movable pulleys are acting like a force multiplier, one problem is that what actually here effort we need to apply upward direction. So applying the effort upward direction is not so easy. But here we have to use single movable pulley as a force multiplier, but effort direction should be changed. It is possible only when we combine single movable pulley with a single fixed pulley, and you may get one out. So will there be any change in the mechanical advantage velocity ratio? No, children. So this entire system, children, here mechanical advantage is equal to 2 only, velocity ratio is equal to 2 only. There won't be any change in the mechanical advantage and velocity ratio. Then what is the advantage? Now the effort direction can be downward direction. Clear? Fine. Now come to the combination of single fixed pulley with the many single movable pulleys. Many means what, children? Yes. So you can apply more than one. Where is here duster? Let me find out. Yes, here I got it. So let me erase this. Let me erase this also. Okay, fine, children. Now look at here. For such a system, how can we find the mechanical advantage and velocity ratio? On common formula is there. Mechanical advantage is equal to 2 power n and velocity ratio is equal to 2 power n. Here n is what? Here number of single movable pulleys. That's it. How many number of movable pulleys are there? 1, 2. In this case, children. So then it is 2 power 2. This will be 4. So this also 2 power 2. It will be 4. For suppose if there are 3 movable pulleys, 2 power 3, 8. 2 power 3, 8. In ideal case only, mechanical advantage is equal to velocity ratio. And another combination is what, children? Block and tackle system. What is a block? The metallic frame in which pulleys are arranged is called block. Tackle is what? A string which connects the number of pulleys in a different blocks. Here we have two types of blocks, children. Movable and what we can say fixed one actually, means upper block and a lower block. Upper block is a fixed, lower block is a movable. Then how can we draw this block and tackle system? Yes, in general in exam they will give you velocity ratio 3, velocity ratio 4, velocity ratio 5 like this. So here velocity ratio gives the number of pulleys. If velocity ratio 3, there should be 3 pulleys. If there are velocity ratio is 4, there must be 4 pulleys. If velocity ratio 5 pulleys must be there. But remember one thing, if there are even number of pulleys, no problem. In upper block and lower block will be having equal number of pulleys. But if there are odd number of pulleys, upper block is always having one extra pulley than lower block. And when you are drawing these diagrams, you should be very careful that here string should be straight, and each and every segment of the string you must show the tension that to upward direction only, and load direction always should be shown downward direction. Then how to find the mechanical advantage of this system, children? Look at here. Here effort is balanced by tension. Okay, effort is balanced by tension, and load is balanced by 3 segments of string, that is load is equal to 3T. So in ideal case, this is I think mechanical advantage is equal to, we know that load by effort, that is 3T by T. So T cancel, it will be 3. Now let us calculate in this case also. Here effort is balanced by tension, load is balanced by 1, 2, 3, 4 segments of the tension, 4T. So with this mechanical advantage is equal to load by effort, that is 4T by T. T cancel, so mechanical advantage is equal to 4. Is it clear, children? Yes. And here we can expect one more question also. What is that question? If effort is displaced like this, if effort is displaced by 2 centimeters, then obviously load will be lifted upward direction. So by what height this load is lifted? Okay, which means what? This is effort displacement. Now they are asking us to calculate the load displacement. So we know the formula, right? Velocity ratio is equal to effort displacement by load displacement, and a load displacement is equal to effort displacement by velocity ratio. So effort displacement is 2, load velocity ratio 3, right? 3, it can be 3. So 2 by 3 you have to calculate, that will be the displacement load. Or else, children, they may ask a question like this also. If for example load is lifted by, for example, 4 centimeters, then find the displacement of effort. Find the displacement of effort. So in that case, effort displacement is equal to velocity ratio into load displacement. Velocity ratio is 3, load displacement is given 4. So this will be 12 centimeters. So like this, similar question can be expected to this also. So these are the concepts of these are the concepts of machine. Just copy it, children. Yes, children. Now we discuss the concepts of refraction of light at a plane surfaces. Here the first important point, before going to what a recall one's refraction, here we need to learn about the 2 important words. Let us say 2 important mediums. Okay, na? Rarer medium and denser medium. See, this optically rarer and optically denser we can understand in terms of speed of light. The medium in which speed of light is more than that of other medium is called rarer medium. Whereas the medium in which speed of light is less when compared with the other medium is called denser medium. Children, we know that very well, no other object can travel faster than the light, and the light can travel fastest in a air or vacuum only. So as long as the light is traveling in a particular, only in a single medium, it will go in a straight line path only. But what happens when it enters into the other medium? Definitely there will be change in speed, due to which what will happen? It will deviate from its path, it will bend. This phenomenon only we can call it the refraction of light. So how can we define, children? When light travels from one transparent medium to another transparent medium, what happens? It bends at the interface between the 2 mediums. This phenomenon of light is called refraction. Is it clear? Yes, it's a very important. And here, what happens when light travels from denser to rarer medium? It moves away from the normal. When light travels from rarer medium to denser medium, it slows down, so it moves towards the normal. And during a refraction, children, frequency remains constant. And whereas speed, wavelength, even intensity will change. Okay, this is very important. Now comes to the laws of refraction. Laws of refraction. Children, according to the laws of refraction, incident ray, refracted ray, normal drawn, all will be lying the same plane at a point of incidence. And the second one is that the ratio of sine of angle of incidence to the sine of angle of refraction always remains constant. It is called Snell's law. But here condition is there. It is applicable for a given pair of two media. The moment when medium will change, again that will change. So means we have to keep two mediums a constant. Okay, this constant only we can call it the refractive index. What is the refractive index, children? It is a ratio of speed of the light in a vacuum or air to the speed of the light in a medium. Children, refractive index of the medium can never be less than 1. It is always greater than 1. Why? Because C can never be less than V. Okay, fine. Refractive index, children, depends on the following factors. It depends on the nature of the medium, depends on the temperature, how inversely proportional to the temperature. And third one, color or wavelength. How it depends? Inversely proportional to wavelength. Which means what? For a red color, wavelength is more than violet color. Hence, the refractive index for a given medium is less for red color, more for violet color. Now we see the refraction through the rectangular glass slab, children. Look, here is a rectangular glass slab. Children, here if you can see, this side air is there, here is a glass, again here is air. Which means what? Rarer, denser, rarer. When light moves from air to glass, it bends towards the normal. Again glass to air, it will move away from the normal. The angle between normal and incident ray is called angle of incidence. The angle between normal and emergent ray is called angle of emergence. Here where the important thing is that angle of incidence is always equal to the angle of emergence. Hence, angle of deviation is 0. So, glass slab does not produce any deviation. Rather, it only can shift the light ray. And here one important thing which we have to notice, children. So, there will be some perpendicular distance between emergent ray to the incident ray when extended forward. This perpendicular distance only we can call it a lateral displacement. Lateral displacement. This lateral displacement depends on angle of incidence, thickness of the glass slab, material or refractiveness of the glass slab, and inversely proportional to the wavelength. Which means what? For a red color, wavelength is more. So, lateral displacement is the least. That is how we have to understand. Now, children, refraction through a glass slab. So here, look at here, A, B, C is a what we can do is a glass prism, children. Now here, let us say here is the incident ray. At this point, it is incidenting. Let us say this is the point P, it is incidenting. Here it is entering from air to glass. So definitely it will move towards the normal. This is angle of incidence, here is the angle of refraction. So inside this is a refracted ray. Refracted ray. At this point, it is going glass to air, denser to rarer. So it moves away from the normal. This is called emergent ray. The angle between normal and emergent ray is called angle of emergence. Now this emergent ray, when you extend backward, children, it meets at some point on this vertical path of the light ray such that it makes some angle. This is called angle of deviation. Very, very important. Is it clear? Angle of deviation. Now children, in examination point of view, they might ask the relation between angle of the prism R1 and R2. What is the angle of the prism, children? The angle between two refracting surface of the prism is called angle of the prism. So here A is equal to R1 plus R2, and angle of incidence plus angle of emergence is equal to angle of the prism plus angle of deviation. But in the minimum deviation condition, children, this refracted ray is exactly parallel to the base of the prism. In that condition, R1 is equal to R2, I is equal to E. If you can substitute this, you will get R is equal to A by 2, I is equal to A plus delta M by 2. And we know that just apply the Snell's law at the first refracting surface of the prism. We know that mu is equal to sine I by sine R. So I value we got here this one, R value we got this here, A by 2. Substitute in the Snell's law, mu is equal to sine I by sine, mu is equal to sine I by sine R. In the place of I, in the place of R, we are substituting this value, hence we got this. So in this formula we use to calculate the refractance of given prism. Means in a lab, experimentally we use, experimentally we can calculate. Okay, fine. Now come to the angle of deviation, children. So examination point of view, definitions are very important. What is angle of deviation? Before, actually if there was no prism, children, it had to go like this. But because the prism, it is going in this direction, means deviating with some angle. So the angle through which incident ray gets deviated from its original path is called angle of deviation. Angle of deviation. This angle of deviation depends on, children, angle of the prism, refractive index of the prism, that is the material of the prism, inversely proportional to the wavelength of the light used. But children, if you can see, there is some special relation between angle of deviation and angle of incidence. So you cannot say proportional or inversely proportional. And this graph also very important for examination point of view. Look at here children, as angle of incidence increases, initially angle of deviation is decreasing, takes a minimum value, and further increasing the angle of incidence, the angle of deviation is increasing. Is it clear? Fine children, just make a note of it. Now next we see the total internal reflection condition, critical angle and total reflecting prisms. Just make a note of it. This will go in this direction. Fine children. Now children, let us see first what is shift children. So children, we might have noticed that what happens when a coin is placed in the tub in which water is taken, what happens, the coin appears as if it is shifted, right? Yes children, so that concept only now we will be seeing here. So for suppose here is a water, here object is placed, the depth at which actually it is placed is the real depth, but it due to the refraction it appears as if it shifted upward, it means the image appears here. So the distance between from the surface to the image is called apparent depth. So this is not true actually, just due to the refraction it appears like that. Then what is shift children? The height through which it is appears as if it is lifted upward direction is actually shift. So here also in terms of real depth, in terms of apparent depth, refractive index can be defined. How to define? Refractive index is a ratio of real depth to the apparent depth. And children here, how to calculate the shift? Real depth minus apparent depth if you can do, then you will get the shift. So shift also can be expressed in terms of real depth and mu. And here one important thing children. So for a 1 mark question, they may ask you to find the shift in the case of glass and in the case of water. So directly you can use in the case of glass, shift is equal to Rd by 3. In the case of water, shift is equal to Rd by 4. How we got here? Just here you substitute the refractive index of glass, you will get this. Here you find the refractive index of water, you will get this. Okay, fine. So shift depends on here refractive index of the medium. More the refractive index, more the shift. It also depends on the thickness of the medium. More is the thickness, more is the shift. It is inversely proportional wavelength. More is the wavelength, shift is less. So which means what? Which color will what a shift will show more shift? Violet color will show more shift. Done? Fine. Now come to the critical angle. Very important. Children, see, whenever light incidents normal to the interface between the two mediums, it will go undeviated. That is a no refraction case. And you look at here. So a light ray is moving from denser to rarer medium such a way that what is happening, so it is incidenting with certain angle such a way that the light ray grazes the interface, hence angle of refraction will be 90 degrees. That particular angle of incidence we can call the critical angle. I repeat once again, the angle of incidence in a denser medium for which angle of refraction in a rarer medium is 90 degrees is called critical angle. And this critical angle also related to the refractive index. How? Mu is equal to 1 by sin c. This is a very important. In exam they might ask you to write the relation. And the critical angle depends on two factors. It depends on wavelength. Okay, it also depends on the temperature. So for a red color, critical angle will be more. For a violet color, critical angle will be less. Now comes to the total internal reflection. Children, to occur total internal reflection, light ray should fulfill two conditions. What are the two conditions here? Light must travel from denser to rarer medium. Light must travel from denser to rarer medium. And angle of incidence must be greater than the critical angle. So in exam they might ask this diagram or this diagram. Look at here. Let us say this light ray A. This light ray A, as it is incident normal, it will go undeviated. Whereas light ray B, children, it is incident with the critical angle, so it's grazes surface. Now if you can see light ray D, because see already we use for critical angle, right? I am not using that. So it is incident with the, see, it is going from denser to rarer, and definitely this angle is more than critical angle, right? So light ray is coming back to the same medium only. This phenomenon only we can call it the total internal reflection. Children, in exam they might ask a question. So what is the difference between total internal reflection and normal reflection? Children, during a normal reflection, some amount of light energy is absorbed. But whereas during a total internal reflection, 0% means no energy is absorbed. Whereas due to the normal reflection, whatever the image which you will get, it may not have that much brightness. But whereas due to the total internal reflection, whatever the image which you will get, it will be 100%, it will be having 100% brightness. Why? there is no loss of energy, right? Okay, na? Fine, children. Now, so let us see the occurrence of total internal reflection in a prisms, so called total reflecting prism. Total reflecting prism. Children, examination point of view, these are very important. So before going to understand this, one thing we should know that, what is that? The critical angle for glass air interface is 42 degrees. Very, very, very important. The critical angle for glass air interface is 42 degrees. Now let us take a total reflecting prism. These are the right angle isosceles prisms, which means what? One angle will be 90 degrees, other two are 45. For suppose, if a light is incidenting normal to the AB, then it will go undeviated. But at this point, let us say P, children, what is happening? It is trying to go from glass to air, that is denser to rarer. And let us see, this is 90, it is 45, this will be 45. Obviously, this will be how much, children? 45 degrees, which means what? Angle of incidence is greater than critical angle. So here two conditions are fulfilled. Then what will happen? Light ray will undergo total interreflection. So by default, it will become normal to AC, so that it will go undeviated. This case of the total reflected prism is used in a periscopes. Done. So this is actually here how much deviation? 45 plus 45. So here angle of deviation is 90 degrees. Now come to the here. Same thing, but this time light ray is incidenting normal to the BC. Right one, BC. So that what it will go undeviated. Let us say the point P. At this point P, light is trying to go from glass to air, that is denser to rarer. If you find here angle, this angle, here is 45. Obviously, this angle of incidence will be 45 degrees, which means what? Angle of incidence is greater than critical angle. So it will undergo total interreflection. By default, it will go to the parallel to the base of the prism, and same thing happens at a Q also. At a Q also, total interreflection will take place. Finally, the light ray will go undeviate, means will emerge normal to the BC. Here 45, 90 plus 90. So total deviation is 180 degrees. So this case of the prism is used in binoculars and even cameras also we can use. Done. Fine. Now let us see the total interreflection in equilateral prism. Equilateral prism means what? All angles are equal. 60, 60, 60. Now children here. So look at this. Here the light is inciding normal to the AB. So it will go undeviated till this point. At this point, it is trying to go from glass to air, that is denser to rarer. First condition fulfilled. This is 90, 60, this is 30. Obviously, this angle of incidence is 60 degrees. Hence, it will undergo total interreflection. By default, this light ray will be normal to BC, so it will go undeviated. Now, total interreflection in 30 degrees, 90 degrees, 60 degrees angled prism. So here light ray is incidenting normal to AB, so it will go undeviated at this point, children. Here this is 90, 60, it is 30. Obviously this angle will be 60 degrees. 60 degrees is greater than the critical angle. So at this point P, light is going from denser to rarer and angle of incidence is greater than critical angle. Then obviously total interreflection will take place. And here with the same 60 degrees will undergo here. At this point, if you will find the angle of incidence will be 30 degrees. So it's very important. At this point, light is going from glass to air, that is denser to rarer only. But angle of incidence is less than the critical angle. Hence, normal refraction, glass to air, it will go away from the normal. Clear? So these are the concepts of what we can say refraction of light at a plane surfaces. Okay, na? Just copy it. Now we revise the concepts of refraction through a lens. Children, first of all, let us recall what is a lens. Lens is a transparent refracting medium consisting of or bounded by either one or two spherical surfaces. Sometimes one might be plane surface, another might be what we can say spherical surface. Here we have two types of lenses, children. Convex lens, concave lens we have. Convex lens is also called as a converging lens, whereas concave lens is also called as diverging lens. And what is the main difference between convex lens and concave lens, children? Here convex lens in the middle it is thick, at the periphery it is thin, whereas concave lens in middle it is thin, whereas at edges it is at a periphery it is a thick. Under convex lens, children, we have biconvex lens or double convex lens. If the radius of curvatures are equal, we also can call it as a equiconvex lens. Then we have plano-convex lens, concavo-convex lens. Under concave lens children, we have biconcave lens or double concave lens. And in that case, if radius of curvatures are equal, it is also called as what we can say equiconcave lens. Then we have plano-concave lens and convexo-concave lens. Children, before going to discuss about the ray diagrams and what the principal is in ray diagrams, we need to recall the terms related to the lens. So children, before that, here you should not forget one thing. What is that here? The radius, the curved surface of a lens are a part of a halo, some sphere, right? So that we have to keep in our mind. So first let us recall what is the center of curvature. The center of a glass halo sphere in which or we can say curved surface of a lens is a part is called center of curvature. In general, there will be two center of curvatures. The line which is joining the center of curvature of the lens is called principal axis. And one more important term is that here optical center. Some people can go to the optic center also. What is the optic center, children? The point on the principal axis of a lens such a way that the line or the light ray which is directed towards it will go undeviated. So these are very important. Then children, what is a focus? Principal focus or principal foci or simply focus? Children, the point on the principal axis where after refraction either light rays meet or appear to meet, that point only we can call it as a principal focus. In general, for a lens, there will be two focus on two sides. Then what is a focal length, children? The distance between optic center to the focus of the lens is called focal length. Clear? Fine, children. Next, focal plane. The plane which is passing through the focus and perpendicular to the principal axis is called focal plane. So these are the terms which we have to remember. Is it clear, children? Fine. And here, children, as we discussed, we recalled about the focal length, children. Here one important thing is that here focal length depends on two factors. It depends on radius of curvatures of the lens. Okay. And the second is that the medium, surrounding medium, the medium in which it is placed is very important. Children, what happens if half of the lens is covered with a non-transparent cover or a material? Will there be any change in its focal length? No, children. If half of the lens is covered with a non-transparent material, focal length won't change. Only the intensity of the image will decrease. And one more important thing is that here, other than air, if you can place a lens in any other medium, its focal length increases. Example, water. What happens when a lens is placed in a water, children? Yes, its focal length increases. So these are the important terms related to the lens. Clear? Fine, children. So if you want to draw effective ray diagrams by a convex lens or a concave lens, we should understand about principal rays which are required. Children, the minimum number of principal rays required to make a ray diagram are 2. Let us see once. So principal rays, first we will see for convex lens, children. If any light ray is passing through the optic center, will go undeviated. And if any light ray is coming parallel to the principal axis, after refraction, it passes through the focus. Whereas, if any light ray is passing through the focus, after refraction, it will go parallel to the principal axis. So these are the principal rays for convex lens. Come to the concave lens, children. If like similar to the convex lens, if the light ray which is passing through the optic center, children, as we know already, will go undeviated. The second one is that for concave lens, if any light ray is coming parallel to the principal axis, after refraction, it will get diverged, but it appears as if it is coming from this focus. This is called second focus. This we will consider the focus actually. Okay, fine. And third one, children, if any light ray is directed towards the focus, after refraction, it will go parallel to the principal axis. Here one important thing is that, children, here convex lens has real focus, concave lens has virtual focus. Clear? Fine. Now we see the ray diagrams of a convex lens and the characteristics of the image formed by convex lens. Children, the first case, object is placed at infinity. Whenever object is placed at infinity, children, we get a parallel beam of light rays. So in this case, where the light rays are meeting? At a focus. So what are the characteristics in the first case when the object is placed at infinity, children? Image is formed at focus. As the light rays are meeting, it is a real. By default is inverted and it is a highly diminished. The second one, object is placed beyond 2f1. When object is placed beyond 2f1, children, image is formed between f2 and 2f2. It is a real and inverted and smaller than object. I mean, it is a diminished image. Third one, when the object is placed at a 2f1 children, image also formed at a 2f2 only, and it is inverted, and size of the image is equal to the size of the object. And the fourth one children, when the object is placed between 2f1 and f1, image is formed beyond 2f1 is the real, inverted, enlarged than object. Fifth case children here, when object is placed at focus, so we are getting these refracted rays will be parallel to each other. So parallel rays are expected to meet at infinity such that it is a real, inverted, highly magnified. And the sixth one is a very important children. Very means very much important. So when object is placed between focus and optic center, image is from same side. That too virtual and erect. So the first 5 cases real and inverted. Sixth case it is where object is placed between focus and optic center, virtual, erect and enlarged. This case of the convex lens is used as a simple microscope or a reading glass, we can say that, and it is also used to overcome the hypermetropia. Clear? Fine. Now children, we see the image formation by a concave lens and a characteristics. First one children, can I erase this because we need space? Yes children. So here the first one is for concave lens is that when object is placed at infinity, we are getting a parallel beam of light rays. After refraction, light rays will get diverged. They do not meet. When they extend back, they appear to meet at the second focus. So here image is formed. So characteristics are, it is a virtual, erect, highly diminished. And the second case children, it is anywhere between infinity and optic center children. Very important, anywhere you can put. So then what happens, this is a very means very much important, because characteristics are always same. It's a O, let us say it's a F2, here is 2F2, this side it is F1, and here is a 2F. Anywhere you can place object. Okay, let me put object here. Okay, here the light rays are coming like this. A, B. Look at here. So if object is placed anywhere between infinity and optic center children, remember that. So here light, after refraction, light rays are getting diverged, but when you extend back, they are appearing to meet between F2 and O. Means children, the very important thing is that image is from same side of the object, but always between object and optic center. It is a virtual, erect and diminished. Here one important thing which we have to notice. In the sixth case, convex lens forms virtual image, and in all cases, means other than this, it forms virtual image only. What is the difference between these two virtual images? For a convex lens children, the virtual image is formed, it is enlarged, and it is formed beyond object. But here between object and optic center, and it is a what we can say is a diminished image. So these are the image formation and the characteristics of the image formed by convex lens and a concave lens. Now children, we need to, so here as we have done with, let us recall once again sign convention rules. Concave lens. Yes children. Now comes to the sign convention children. So without sign convention rules, without knowing, you cannot do the numericals based on the lenses children. So according to the sign convention rules children, here optic center of the lens is considered as the origin, such a way that all horizontal measurements must be taken from the optic center only. And the third point is that here, the distances taken in the direction of incident ray are positive, opposite direction are taken as a negative. And the measurements taken above the principal axis are positive and below the principal axis are negative. So as per the sign convention rule children, let us see, for a real image, object distance is negative, image distance is positive, object height is positive, image height is positive. For a virtual image children, object distance, image distance both are negative, object height, image height both are positive. And one more very important thing is that here, for a convex lens, the focal length is always positive. For a concave lens, focal length is always negative. Now next, lens formulae. This gives the relation between focal length, image distance, object distance. That is 1 by f is equal to 1 by v minus 1 by u. Now comes to the linear magnification, children. What is the linear magnification? The ratio of image height to the object height or image distance to the object distance is called linear magnification. So here is a formula. From these two, we also can equate hi by h naught is equal to v by u. Children, these are very important when solving the numerical. And what is the importance of linear magnification? So by knowing the sign of the linear magnification, we can come to know the nature of the image, and by knowing the value of the image linear magnification, we will come to know about the size of the image formed. Children, so if linear magnification is a negative, it is a real image, or else for a real image linear magnification is negative, for a virtual image linear magnification is positive. If linear magnification is less than 1, it is diminished image. If it is equal to 1, it is the same size of the same size as that of the object. If a linear magnification is it is a greater than 1, it is a enlarged image. Clear? Fine. And for convex lens, because we know that convex lens forms real image and as well as virtual image. So it's a sign. It's for convex lens, m can be positive, m can be negative. And we also know that what we can say, convex lens forms diminished image, equal size image, enlarged image. That's what linear magnification can be less than 1, can be equal to 1, can be greater than 1. But whereas comes to the concave lens, children, concave lens always forms virtual and diminished. That's what for concave lens, linear magnification is always less than 1 and positive. Clear? Fine. Now next come to the power of a lens. So what is the power of a lens? It's the ability to diverge or converge the incident light ray which is falling on a lens is called what actually? Power of a lens. A particular lens is a converging or diverging more. Definitely it is said to be having more power. And the power of a lens is inversely proportional to the focal length of the lens. Children, so how both are related? Power is equal to 1 by f, focal length, it is in meters, or focal length is equal to 100 by f, here f is in centimeters. Then what are the units of power, children? Power of a lens, it is measured in diopters. And here one very important thing is that here for converging lens, power is positive, for a diverging lens, power is a negative. And whereas for a thin lens, I think, here I wrote wrong. For a thin lens, power will be less, focal length will be more. Whereas for a thick lens, power will be more, whereas focal length will be less. Done? Fine. Comes to the magnifying glass. Children, we know that what is magnifying glass or simple microscope. What is its use actually? Yes, it is used to see the tiny objects. So that it can be seen enlarged, right? So here convex lens with a short focal length is preferred as a magnifying glass or a simple microscope. And we know that in the 60th case of the convex lens, children, when the object is placed between focus and optic center, it forms virtual and enlarged image. That is the reason why convex lens with a short focal length is preferred as a magnifying glass or a simple microscope. And magnifying power of a simple microscope is given by 1 plus d by f. So here magnifying power is inversely proportional to focal length, which means what? How can we increase the magnifying power of a simple microscope, children? By using a convex lens of short focal length, or by using the convex lens with a thick one. It's a thick, so thick convex lens should be preferred so as to have a more magnifying power. And here the applications of convex and a concave lens. Children, first we will see the convex lens applications. Convex lens is used as a burning glass. It is used in a camera lens. It is used in a terrestrial, what we can say, a telescope. It is also used in slide projectors. It is used in spectroscopy, and it is also used as a simple microscope, and even it is used to overcome the hypermetropia. And it comes to the concave lens, concave lens applications. It is used in a what we can say Galilean telescope, and it is also used to overcome the myopia. Is it clear? So these are the concepts of refraction through a lens. Now we see the concepts of in a light part, refraction to plane surface is over, refraction through a lens is over. The last part, a small portion it is, and a scoring. It's very easy to understand also. Okay, fine. In this, children, first deviation produced by a prism means it is a monochromatic light, children. This is what actually monochromatic light. So what will happen? Already we studied in plane surfaces. Just let us recall here. So here, due to the refraction, it is bending towards the normal. Again here, due to the refraction from glass to air, it is going away from the normal here. If you can produce this emergent ray backward, here you can notice this is the angle of deviation. So what is the angle of deviation? The angle through which incident light ray gets deviated from its original path is called angle of deviation. At a first refracting surface, a delta 1 deviation produced. At a second refracting surface, delta 2. Delta is the total deviation produced, is obtained by delta 1 plus delta 2. And on which factor does the angle of deviation depends, children? Angle of deviation depends on the angle of the prism, refractive index of the prism, wavelength of the light, whatever it is incidenting, and with what angle it is incidenting. Clear? Fine. Now comes the dispersion. Children, here is the monochromatic light, but here is the white light. Children, we know that here, when white light is passed through a prism, it gets splitted into its constituent colors. This phenomena of light, this phenomena of splitting of white light when it is passed through a glass prism is called dispersion. Then what is the cause of the dispersion, children? Yes, different wavelengths will travel with different speeds. For example, wavelength of a red color is more, deviates less, so travels faster. And whereas a wavelength of violet color is less, deviates more, travels less, or travels with a less speed. Here you can see here, yes, the deviation produced by violet color is more than of the red color. And here two important points which we have noticed. At a first refracting surface, dispersion and deviation both will take place, but whereas at the second refracting surface, only deviation is taking place. And the band of colors, band of wavelengths so obtained in the screen or is called actually spectrum. Okay, na? Done, children. Now come to the electromagnetic spectrum. Children, when sunlight is passed through the prism, we are getting a VIBGYOR colors, but it doesn't mean that, do you think that only these colors are present in sunlight? No, it is not that. Many experiments prove that beyond violet color, beyond even red color, so many other radiations are possible. Together only we can call it. Means those radiations are invisible. This is invisible. This is a visible. Those radiations are invisible. Visible spectrum plus invisible spectrum. Together we can call it the electromagnetic spectrum. Here till date we have this one: gamma, X-rays, UV, VIBGYOR, infrared, micro, radio. It is an increasing order of wavelengths. This is a increasing order of frequencies. Then what are the common properties of electromagnetic waves, children? Yes, these electromagnetic waves do not require a medium. They can travel through vacuum. All can travel with the same speed in air and a vacuum. That is with a 3 into 10 power 8 meter per second. And these electromagnetic waves do not get deviated in an electric field and a magnetic field. Electric field and magnetic field. And these are transverse in nature because electric and magnetic fields are oscillating perpendicular to each other and perpendicular to the direction of propagation of electromagnetic wave. And like light, children, these electromagnetic waves can exhibit reflection and refraction. Okay, na? Fine, children. Now let us see. So in a shortcut, let us see about the radiations. So gamma radiation, children, the wavelength range is less than 0.1 angstrom or 0.01 nanometer. These gamma radiations are emitted during the radioactive emissions, which we will be learning in a radioactive decays and all these things. And here gamma rays are very used in a radiotherapy to cure the cancer, right, due to their high penetrating powers. Next one is X-rays. The wavelength range is 0.1 angstrom to the 100 angstrom and or 0.01 to the 10 nanometer. Children, especially actually generally in a examination, what they are trying to ask, sometimes they are asking the questions based on the wavelength, mostly gamma and X-ray. Please remember this. And X-rays are very useful in a radiography, means to detect the fractures in a bone and even to study the atomic arrangement of crystal. These X-rays are used. Next one is UV radiation. The wavelength range is 100 to 400 angstroms. 100 to 400 angstroms. When solution of silver chloride is exposed to the UV radiation, first they will turn into this solution of silver chloride will turn into violet color, then finally it will turn into dark brown. So just because of their action on dyes only they are recognized. They can be detected easily. Okay. And how can we obtain the UV spectrum, children? By using quartz prism. Quartz prism. Why not glass prism? Because glass prism can absorb all radiations. Why only quartz prism, children? Here quartz prism can absorb all radiation except UV radiation, so that UV spectrum is obtained. And here what are the applications? Yes, they are used to check the purity of germs and eggs, the production of D vitamin, the sterilization, means in a surgery tools, sterilization also it can be used. And infrared radiations. So between we have VIBGYOR, right? What is the wavelength range of VIBGYOR, children? It is a 4000 angstroms to 8,000 angstroms. So what is the use of the VIBGR? Yes, which makes the things visible, right? Without VIBGR, we can't see the things only. Now comes to the infrared radiations. These are also called as heat radiations, children. So what are the sources of these? Hot bodies. How can we detect the infrared radiation? Yes, by using blackened bulb thermometer. But how can we get the infrared spectrum, children? Yes, here rock salt prism. Here it is not written. Rock salt prism is used to obtain the infrared spectrum. And the applications, children. These infrared radiations are used as a signals during a war. But why? In exam they will ask a question. Why they are used? Because they are invisible and they are not absorbed by the medium much. Okay. And they are used in a night photography. What is the reason? And through where there is a fist and fog also it can be used. Because they will scatter least. Okay, no? Fine. Now the microwaves, the wavelength range is 10 power 7 to 10 power 10 angstroms. These are used in satellite communication. In a microwave ovens also these are used. And the last one is not in this chapter. In this electromagnetic spectrum I am talking. So radio waves wavelength range is greater than 10 power 10 angstroms. And they are used in a radar communication. Also used in radio television communication. What we call the transmission, you know. These are all used. Okay, so examination point of view, applications are important. Just try to, especially here, try to remember the wavelength ranges here. Okay, no? And mostly applications of UV radiations and what we can say infrared radiations are very important examination point of view. Just copy this. The last topic in this chapter is scattering. Okay, now just copy this. We'll discuss. So now we see the concept of scattering of light, children. So when a sunlight enters into the atmosphere, in atmosphere what will be there? Dust particles will be there, water molecules will be there. So what will happen, you know, when light incidents on these particles, that light is absorbed and re-emitted. So this process only we can call it the scattering of light. Means the process of absorption of energy and re-emission of energy of light. Only we can call it as a scattering of light. And here, children, here of course two types of scattering will be there. See, in all situations scattering won't happen in the same place, same type right here. So here, before going to learn about the application of the scattering, actually first we see one important thing. The particle on which light is incidenting, the size of that particle is so-called scatter size is very important. If a scatter size is less than that of the wavelength of the light which is falling on it, then only one particular light gets scattered. So this is obeyed. That is what? Intensity of a scattering light is inversely proportional wavelength, fourth power of the wavelength of the color. Which means what here? More the wavelength, less is a scattering. Less is the intensity of scattering. If less is the wavelength, more is the intensity of scattering. But whereas, if the size of the scatter is more than that of the wavelength of the color, then all colors, all light colors will get scattered to the same extent. Now let us see the applications here. Red color of sun during sunset and sunrise. During the sunrise and sunset, children, light has to travel a long distance, first point. And here all colors will get scattered except red. Why? Because red color wavelength is more. So that what will happen? Red color will reach our eye without getting scattered. So all colors are coming. Okay, but we are receiving only red color. So that we are feeling sun is in red color during our sunrise and sunset. Okay, because red light will scatter least. Second, blue color of sky. So actually compared to the blue color, violet color will get scattered more, right? So sky would appear in a violet, but why not in why only in a blue color? Because the violet color will get scattered more, children. Violet color will get scattered more, but the thing is that the amount of violet color which will get scattered, means in a sun spectrum, if you can it is, the amount of violet color will be less, that portion, than that of the blue color. So that the next violet is what actually indigo will be there, but next blue. So compare with indigo and what we call violet and indigo, blue portion is more, so that blue color will dominate. That is the reason why sky appears blue color. And why only more blue color is scattered? Because the size of the nitrogen oxygen almost which is nearly equal to the blue color. Okay, now fine. Next, red light for a danger signal. Children, red color is not a danger signal, but why we are using as a danger signal, so just we are thinking that we are approaching the signal. So as red color has a maximum wavelength, it can travel with a fast, speed is more, it will scatter least, so that it can reach the person, the driver very easily, so that the red color signal is given, so that yes, as it is a stopping signal, we will try to stop. other than red color, if you can use any other color, they won't reach our eye only. Mean the moment when you reach traffic signals, you won't realize that its stopping signal is given. Okay, na? Fine, children. Now comes to the white color of clouds. So how does the clouds appear, children? They appear white only. But why they are not in some other color? Because these clouds are consisting of water molecules and dust particles whose size is very much bigger than that of the wavelength of the light. So what will happen? All colors will scattered equally. So same moment, all colors, all scattered light will reach our eye. The combination of all colors is what actually white. That is the reason why clouds appear white. And the last point, which is very important thing, is that yes, from moon surface, if you can look at the sky, that atmosphere, how does that sky appears? Black, dark. What is the reason? As there is no atmosphere, so that there is no scattering. So we all are feeling, because these colors main is what? Scattering only, right? So there is no atmosphere, obviously there is no scattering. So these are the concepts of spectrum chapter. Just copy it. Next we'll proceed to the sound chapter. Okay, na? Copy it. Yes, children. Now we discuss the concepts of sound, children. Children, what is sound? Sound is a form of energy. When it reaches our ear, it produces, or we feel, a sensation of hearing. And we know that vibrating bodies will produce sound. But can we hear the vibrating sound produced by all vibrating bodies? No, children. So the sounds with a less than 20 Hz frequency are called infrasonics. The sound with a greater than 20 Hz frequency are called ultrasonic. These sounds we can't hear. Then what is the audible range of the sound, children? Only 20 Hz to 20,000 Hz. Children, as sound can propagate in the form of wave, we need to recall about a wave. What is a wave, children? Here, a disturbance created in the medium which can travel in all directions with equal speed is called wave. But one important thing is that, children, during the propagation of wave, particles of the medium, they do not vibrate. Rather, they do not move. Rather, they vibrate from their mean positions. So it depends for the propagation of wave whether medium is required or not. We have two types of wave: mechanical waves and transfer waves. What are mechanical waves? The waves which require material medium for the propagation are called mechanical waves. For electromagnetic waves, children, what we can say, material medium is not at all required. Now, based on the vibration, how the particles are vibrating during the propagation of wave, waves are classified into two categories: longitudinal wave, transfer wave. What are longitudinal wave, children? Here, the wave in which the particles of the medium vibrate parallel to the direction of propagation of wave is called longitudinal wave. During the propagation of longitudinal waves, children, compressions and rarefactions are formed. And these longitudinal waves can propagate through solids, liquids, gases. Comes to the transfer waves, children. The wave in which particles of the medium vibrate perpendicular to the direction of propagation of wave is called transfer wave. And during the propagation of transfer waves, crust and troughs are formed. These transfer waves can propagate through the gases and only on the surface of the liquids only. Clear? Fine. Then how to calculate the speed of the longitudinal wave? Example, sound wave in air comes under longitudinal wave, right? Yes, here. And children, the sound waves in the solids comes under transfer waves. Don't get confused. So V is equal to here gamma P by rho. And children, here the speed of the sound, on which factor does the speed of sound depends? Speed of sound depends on temperature, depends on density of the medium, and depends on the humidity, and depends on the direction of wind also. And here speed of the sound does not depend on pressure, frequency, wavelength and amplitude. Clear? Fine. Now come to children. So what are the waves which are produced on the stretched string? Comes under transfer wave. So the speed of the transfer wave is V is equal to tension by M. M is what here? Linear mass density, mass per unit length. Okay, na? Fine, children. Next, reflection of sound, children. So like light, sound also will undergo reflection. But here one important condition is there. What is that? So to happen this reflection of sound, children, the size of the object should be very much bigger than that of the wavelength of the sound. And even like light, children, sound also will undergo refraction. So during the refraction of sound, children, frequency remains constant. But during the refraction of sound, what we can say, speed, wavelength, intensity will change like a light only. Comes to the echo. So some students, they will have a confusion with the reflection of sound and echo, children. Please try to understand. all echoes are not a echo, all reflection of sound can't be echo actually. Try to understand, because some conditions are there. When these conditions are fulfilled, then only reflection of sound can be a echo. So what is the echo, children? Here the reflected sound which is heard from a distant object when original sound has ceased is called echo. So look at here, for example, here a person is producing a sound and it is D, the distance between obstacle and a source of sound, children. This what we can sound is going, this is called incident ray, the incident sound wave, it is a reflected sound wave. So during in a time interval t, children, in a time t, it is traveling d plus d, total 2d, that's what speed is equal to 2d by time actually. So this formula is very important in order to solve the numericals based on the echo. Then what are the conditions, children? Yes, here. So the time between original sound and the reflected sound minimum should be 0.1 or can be greater than 1 also. If the reflected sound is reaching our ear less than 0.1 second, so we cannot hear properly. Okay, fine. And second one, in air, the minimum distance between the obstacle and source should be 17 meters, whereas in a water, it is 72.5 meters. And third one is that the size of the obstacle should be very much greater than that of the wavelength of the sound. And the fourth one is that here the intensity of a instant sound should be a very high, such a way that it should get reflected back and should be heard. So these are the conditions. Okay, now comes to the applications, children. So mostly we can, so in a echo what are related applications, children, generally we will be using a sonars only. Sorry, not sonar, ultrasonics. Why we are using ultrasonics? Because of their special properties. So ultrasonics, they are high directivity, they are of high directivity, they are confined to a narrow beam and they will travel through the medium long distances without getting absorbed much. Because of these reasons, ultrasounds are used in many applications. And here come to the sonar, children. So in a sonar, yes, concept of echo is used where we will be using the ultrasonics. What is sonar? Sound navigation and ranging. And here radar also we can use a concept of echo. What is the radar? So radio detection and ranging. But in radar, children, we use electromagnetic waves. In other applications, again ultrasonics only. So we know that bats and dolphins, they can produce a ultrasound and they can use the echo concept to find what to reach their destinations, to find the prey and obstacles and all these things. And it is also used, what we can, this echo concept and a sonar, what we can say ultrasonics, they are used in ultrasonography and even can be used in echocardiography. Okay, fine, children. So this is mostly application oriented only. Okay, now fine. Now we discuss the types of vibrations during journey. Fine, children. Yes, first, what are natural vibrations, children? So the vibrations which can happen in the absence of an external force, means the periodic vibrations in the absence of any external force acting on it are called natural vibrations. Example, children, the oscillations of a pendulum in a vacuum, vibrations of a tuning fork in a vacuum, means any vibrations of any object happening in a vacuum comes under natural vibrations. And the specialty is that here, as there is no external force, obviously the amplitude of the natural vibrations remains constant. So this is how displacement time graph of the natural vibration will be very, very important. Means amplitude remains, as time passes, amplitude remains constant. Okay, fine. And here one more important thing, children, the frequency in a time period depends on the size and shape of an object which is undergoing natural vibrations. Clear? Fine. Then examples, children. Yes. For example, the frequency of a simple pendulum is 1 by 2 pi into square root of g by l. Means what? It is inversely proportional length. By changing the length of a simple pendulum, we can change its natural frequency. And second one is spring mass system here. So for a spring mass system, frequency is equal to 1 by 2 pi into square root of k by f. Means by changing the k, spring constant, and a mass, we can change the frequency of the spring mass system. The third one is the string in an instrument, children. For that frequency is equal to 1 by 2l into square root of 2 by pi r square d, which means what here? This frequency depends on length of the string, tension of the string, r is thickness of the string, d is density of the string. Clear? And the one more very, very important thing, children, here, if any string is stretched between the two rigid supports and it is plugged at a different points, definitely we will have a different modes of vibrations. Then what is the frequency of the different modes of vibration, children? Here it is. So f1 is to f2 is to f3, means we are initially, means first we will plug in the middle, next 1/4, next 1/6. Then the frequency ratio is 1:2:3, and the ratio of the modes of vibration of the wavelengths is 6:3:2. Okay, fine. Next, damped vibrations, children. So the periodic vibrations in the presence of external what we can say resistive force, so that the amplitude will be decreasing. So simply we can say that here the periodic vibrations with a decreasing amplitudes in the presence of external medium or external resistive force are called damped vibrations. Example, oscillations of pendulum in air, vibrations of tuning fork in air. And the very important thing, children, here, due to the resistive force, the amplitude keeps on decreasing, means as time passes amplitude will be decreasing. Look at here, as time is passing the amplitude is decreasing. Finally these oscillations are ceased. What is the reason? Because energy is lost against the frictional force. Clear? Fine, children. Now come to the forced vibrations. What are forced vibrations? The vibrations of any object under the influence of external periodic force, means repeatedly the force is applied, then body is undergoing some vibration. Those vibrations are called forced vibrations. Example, so if like what the vibrating tuning fork, when it is pressed against the what we can say a table, so big sound is heard actually. So there in that case what we can say, the table is forced to do the vibrations. When we are beating the drum, that membrane of drum will be there, it will be vibrating. Yes, it is in what we can, it is executing forced vibrations. And here, children, we have one special case, resonance. Resonance is a special case of forced vibrations where the natural frequency of the vibrating body matches with the frequency of the external force applied. Children, in exam they may ask a question, what is the condition to occur resonance? So the natural frequency of the vibrating body must match with the frequency of the external periodic force applied. Done. And during this phenomena, so called resonance, children, a louder sound is heard. Why? Because amplitude increases. As amplitude is increasing, louder sound is heard. And examination point of view, applications of resonance are very important. Children, while these soldiers are crossing the suspension bridge, they are asked to do, means to not to do the march fast, rather they have to have a casual walk, because if they'll go with a march fast, definitely they apply some force. If time is bad, in a worse situation, the natural frequency of the what we can say suspension bridge might match with the frequency applied by the force of the soldiers. Then what will happen? Suspension bridge will vibrate with the increasing amplitude. It may collapse. It may get collapsed. It may get damaged. And the second one, so in a TV and a radio, children, when we are trying to tune to a particular channel, what we'll try to do? Yes, we are trying to match the frequency of the oscillator with the frequency of the radio waves. And third one, so whenever we are just traveling in particular vehicles at a particular speed, children, we can hear a louder sound, because at that particular speed the frequency of the engine matches with the frequency of the all other vibrating bodies. Natural frequency of the all other vibrating bodies, then they all are in resonance, so that louder sound is heard. Okay, now fine. So these are the types of vibrations. And here the what we can say, the last concept in the sound is what actually? Characteristics of the sound. Wave pattern or waveform. Fine, children. Now look at this. So children, there are three characteristics of sound. The first one is what actually? First one is loudness. Second one is pitch, third one is quality. Children, what is the loudness, children? The characteristics of the sound with which we can differentiate louder sound from a faint one is called loudness. And loudness is how it is related to the intensity. Children, here, what is intensity here? Very, very important. So the amount of energy which is passing per unit area in a 1 second is called intensity actually. So intensity units are watt per meter square. So this is how both loudness and intensity are related. So loudness depends on mainly 4 factors. First one is loudness is proportional to the square of the amplitude. It can be written as L1 by L2 is equal to A1 square by A2 square. It is inversely proportional to the distance between the source of sound and the listener. And it is proportional to the surface area of the vibrating body. And even loudness of a sound also depends on the presence of resonating bodies. Clear, fine. So in exam, like these two waves with the same frequency and the quality will be given. They will ask us to find which one will have more loudness. Obviously, this amplitude is more than this. So obviously, loudness of wave B is greater than loudness of wave A. Clear, fine, children. Now come to the pitch. What is the pitch, children? The characteristics of the sound with which we can distinguish the what we can say acute note from a grave note. Actually, it is called actually pitch. Pitch depends on frequency. More is the frequency, more is the pitch. Less is the frequency, less is the pitch. Now children, look at here. In these two waves, both having same amplitude, wave pattern is same, so quality is same. But here in a second wave, wave B, more number of waves are produced in a second time. So more is the pitch. So definitely more will be the more is the frequency. Obviously more will be the pitch. So here frequency of B is greater than frequency of A. So therefore pitch of B is greater than pitch of A. And the last one is the quality, children. This is a very important. Children, it's a very important thing is that two different musical instruments may produce sound with same loudness and same pitch, but they cannot produce the sound with the same quality or same timbre. So the characteristic of the sound with which we can distinguish the both sounds from a different instruments with the same loudness and the same pitch is what actually called quality. So quality depends on wave pattern, and it also depends on the waveform. So you can see the diagram on the board here. And then first one is the wave pattern of the sound produced by tuning fork, and the second one is the sound pattern produced by the piano. Both will have same loudness, same pitch, but pattern is different. Obviously the quality will be different. And here one important point which you forgot, children, the unit of loudness is a phone, but the level of sound is measured in terms of decibel. Children, if a sound with a the level of sound if exceeds 120 decibels, it causes noise pollution. Children, what is the difference between noise and the music, children? Yes, music means what? The sounds which are produced in a rhythmatic way. But whereas noise, what we can say, when the noise is produced, if a sounds are produced in a disturbance manner, in a disorder, without discipline, we can say that. And with music, we can have that pleasant feel. But whereas with the noise, children, definitely the irritation, we will be getting irritated, and which may lead to some health issues also. Okay, na? So these are the concepts of sound, children. Just make a note of it. Now we discuss the concepts of current, electricity. Children, what is a current here? The rate of flow of charge is called current. That is I is equal to Q by T. If n number of charges are flowing in a time t, then current is equal to n times of charge, that is n E by T. Children, here the SI unit of current is ampere, and here ammeter is a device which is used to measure the current. And the current always flows from higher potential to lower potential. Then what is the potential, children, here? Yes, the potential is what actually here? The amount of work done to bring unit positive charge from infinity to a particular point is called potential. So potential can be written as work done by charge. It is, see children, like a current, potential also scalar, even resistance also scalar. Okay, don't get confused there. Okay, fine, you have to remember. The SI unit of potential is volt, and voltmeter is a device which is used to measure the potential. And even potential difference, children. What is the potential difference here? The amount of work done to move the unit positive charge from one point to another point in an electric circuit is called potential difference. Units are volt, and it is measured by a voltmeter only. Clear? Fine, children. When it comes to the resistance, what is the resistance, children, here? The abstraction given to the flow of charges by the material or by the conductor is called resistance. Mainly there are two reasons, children, for resistance. What is the first reason here? The collisions of electrons with the core of the material. And the second one, the collisions among the electrons itself. And the resistance depends on mainly four factors. It depends on nature of the material, depends on the temperature. In the case of conductor, resistance is proportional to the temperature. In the case of semiconductor, resistance is inversely proportional to temperature. And the third one, resistance is proportional to the length. Resistance is inversely proportional to the area of cross section. So if you can combine these two, these 2 points, you will get R is equal to rho into L by A. What is rho here? Specific resistance or resistivity. Specific resistance or resistivity. So here we can make a resistivity as a subject. So rho is equal to R A by L. What is its SI units are? Ohm meter, children. And here one important thing is that on which factors resistivity depends here. Resistivity depends only on nature of the material and the temperature of the material, but it does not depend on length and area of cross section. Means it doesn't depend on the physical conditions. It's very important. Okay, now fine. Now come to the conductance children here. The reciprocal of resistance is called conductance. Its units are per ohm, what inverse, or mho, or simply Siemens. What is the conductivity? The reciprocal of resistivity is called conductivity. Its units are Siemens meter inverse. So these are the important physical quantities. Now comes to the Ohm's law children. So in exam they might ask a question like this. So name and state the law which gives the relation between current and potential difference. What is that? Actually it is the Ohm's law. So here Ohm's law states that the amount of current flowing through the conductor is directly proportional to the potential difference applied across its ends. That is V is proportional to I. So mathematically we can write V is equal to IR. Children, condition. So very here condition you should not forget, otherwise you won't get mark. What is that condition here? Yes, temperature and physical conditions should remain constant. And here is a circuit diagram for Ohm's law children. Here 2 points we need to remember. Voltmeter always must be connected in a parallel. Ammeter must be connected in a series. Clear? Fine. Based on the Ohm's law children, conductors are classed in two categories. Ohmic conductors, non-ohmic conductors, or ohmic resistors, non-ohmic resistors. What are ohmic conductors? The conductors which obey the Ohm's law are called ohmic conductors. Example, all metals. For ohmic conductors children, we have a VI graph and a IV graph. In both cases, we get a straight line passing through origin only. But difference is that slope. For a VI graph, the slope is resistance. Whereas for IV graph, the resistance, the slope is conductance. This is a point where some students are getting confused. The slope of VI graph will be resistant. The slope of IV graph will be conductance. Don't get confused. Clear? Fine children. Now come to the choice of the material. Children, depends on the application, depends on the use, we will prefer a different material just based on their properties. Comes to the fuse wire children. So whatever the wire which you want to choose as like fuse wire, what are the properties of the fuse wire children? Yes, should have high resistance, low melting point, and this fuse wire is made up of what? Lead and tin. Comes to the filament wire children, it should have high resistance, high melting point, made up of with the tungsten. And heating wire should have high resistance, high melting point, made up of with the nichrome. Connecting wires usually copper or aluminum. So they should have children high melting point but low resistance. Why? They have to carry the current, right? Yes. And the last one is that here standard resistors. So the resistor, the materials whose resistance is independent of the temperature. So example, Constantine manganese. Is it clear? So just copy this topics. Now we will discuss the EMF, terminal voltage, potential drop, and the combination of resistors. Here is calories. Now we try to understand the concept of EMF, terminal voltage, potential drop children. Now if you can see the cell children here. So when the current will flow children, during the flow of current children, charges will be moving. But already we know that in order to move the charges, some work must be done. Now look at it children. Here this is external circuit, here is internal circuit. Let us say from point A, here one charge is there, unit positive charge. In order to move this charge from point A to point B in external circuit, some work must be done. That is W A to B. Whereas inside, to move the charge from B to A, the work done will be BA. Now if we can add these two children, you will get the total work done, right? Yes, obviously. Okay, fine. Now both sides you just divide with the charge Q. It is Q, H, Q. Now look at here. There is a work done to move the charge in external circuit. The work done by the work done per unit charge. What moving the charge in a outside in an external circuit is called terminal voltage. This is what the amount of work done to move the charge, the amount of work done per charge to move only within the circuit is actually potential drop. If you can add these two children, you will get total work done to move the charge in entire circuit is a EMF. So what is EMF children? The amount of work done to move the charge in entire circuit. What is terminal voltage? The amount of work done to move the charge in an external circuit. And even in other terms also we can define. So EMF is defined. So EMF is nothing but the potential difference across the terminals of the cell in an open circuit. Whereas terminal voltage is the potential difference across the terminals of the cell in a closed circuit. Okay, now fine. So with this relation we can write EMF is equal to V plus, that is the terminal voltage plus potential drop. Terminal voltage can be written as I into R external resistance. Potential drop is I into small r internal resistance. So with this we can get an expression total current I is equal to EMF by R plus R. Children, in order to find the total current in the circuit, EMF by total resistance. And here we need to recall, you need to revise about the internal resistance. What is the internal resistance, children? Here the resistance offered by the electrolyte of the cell is called internal resistance. And here one more important thing is that on which factor does the EMF depends? EMF depends on the nature of the electrolyte and the nature of the electrodes. But EMF does not depend on the distance between the electrodes, surface area of the electrodes, amount of an electrolyte what amount of an electrolyte which is taken. Okay, but whereas children, internal resistance depends on the distance between the electrodes, size of the electrodes, temperature of the electrolyte. Clear? Fine, children. Now come to the combination of resistors, children. So here we have a series combination and a parallel combination. When you can say that resistors are cut in series, children, so resistors are said to be in series if same amount of current is flowing. So here is a circuit diagram for a series combination. So in a series combination, current remains constant but potential is divided. So how can we calculate the total resistance? By adding all the resistances of individual resistors. If n number of resistors with the same resistance are connected in series, then effective resistance is equal to n times of R. Children, as we know that potential gets divided across the resistors, then how to calculate the potential here? This is V1 is equal to I into R1 by R1 plus R2, and the V2 is equal to V into R2 by R1 plus R2. Then come to the parallel combination of resistors. When you can say that resistors are connected in parallel, children, if current is divided and potential difference is same across all resistors, which means what here? Potential is constant, difference is constant across all resistors, but current is divided. Current is divided. Then what is the effective resistance, children? 1 by Rp is equal to 1 by R1 plus 1 by R2. This also can be written as like this. Rp is equal to R1 R2 by R1 plus R2. Children, a parallel combination, current gets divided. But how to calculate the I1 and I2? Look at here. So I1 is equal to I R2 by R1 plus R2. I2 is equal to I R1 by R1 plus R2. If n number of resistors with the same resistance are connected in parallel, then effective resistance is given by Rp is equal to R by N. Now come to the electrical energy. Children, electrical energy is the most desired form of energy. But how to calculate that? Look at here. For suppose the resistor R is connected to the battery of voltage V, so that current I is passing in a time T. Then electrical energy. So electrical energy we can represent with a W. Don't get confused like a work. Don't think it is a work. So we can use actually. So W is equal to V into Q, and we know the Q is equal to I into T. So W is equal to VIT. From the Ohm's law, we know V is equal to IR. Then we will get I square RT. And by simplifying, we also get W is equal to V square by R into T. Clear? Fine. What are the essence of electrical energy? Joules only. But commercial units of electrical energy are watt hour and kilowatt hour. 1 watt hour is equal to 3600 joules. 1 kilowatt hour is equal to 3.6 into 10 power 6 joules. Next, electrical power, children, means the rate of supplying of power, the rate of supplying of energy, or the rate at what rate electrical appliance can consume the energy is also called as a power. So power is equal to electrical energy by time. Okay, means in all these expressions, if you can divide with the time, children, you will get the expressions for the electrical power. Children, here power rating of electrical appliance is very important. So what information do we get from the power rating of an electrical appliance? Yes, by knowing the power rating of an electrical appliance, we will come to know that the safe limit of current through a particular device, and even we can calculate the resistance of that particular appliance when it is in use. Done? Fine, children. Now children, how to calculate the electrical energy? So electrical energy can be calculated like this here. It's a power into time, but power must be in kilowatt. Time must be in hours. So whatever the value which you will get, that value you will get in kilowatt hour. Children, kilowatt hour is nothing but actually it's a 1 unit actually. 10 kilowatt hours means 10 units. So hence the cost of electrical energy is equal to number of units into cost per unit. Then which we will get the amount of what you can say money which we are going to pay for the amount of electrical energy which we consumed. Now the last point in this current electricity is what actually it's a whenever, children, remember that whenever current flows through a resistor, okay, if I current passes through a resistor of R in a time T, some amount of heat is produced. That heat produced depends on current, resistance and time. Then how can we calculate that, children? H is equal to I square RT. It is in joule. but 1 joule is equal to 0.24 calories. You substitute that, you will get H is equal to 0.24 into I square RT. It is in calories. So, these are the concepts of current electricity. Yes, now we will be discussing the concepts of household circuits. Mainly in this chapter, children, we have a power transmission, power distribution, safety devices. Children, at a power generating station, power with 11 kV and 50 hertz is generated. But when it reaches to our house, children, it's what is the voltage? 220 volts and 50 hertz. So frequency won't change, but there will be a change in the voltage. And one important thing is that the children, always power with what we can say high voltage, low current is transmitted. Power is always transferred in terms of high voltage and low current. Why low current, children? Low current involves low power loss. That's a very important. So let us see how power transmission will take place. First, power generating station 2, it will go to the grid substation where power is increased to 132 kilovolt. It's very important with the help of step up transformer. So why are we increasing the voltage? Children, already I told you that high voltage involves low current and a low power loss. And from here it will just go to the main substation where power is decreased to 132 to 33 kV. This 33 kV power with the 33 kV is a very useful to the heavy industries. From here we will go to the intermediate substation where power is reduced to 11 kV and it is very useful to the small industries. From here it will go to the city substation where power is reduced to 220 volt with the help of step down transformer, and from here only we get to our houses with the 220 volt 50 hertz. Clear? Fine, children. Again from city substation, how that power is distributed? Look at here. So from power distribution, 3 cables are involved, children. Here live wire, neutral wire, earth wire. Live wire is also called as phase wire and it is at a 220 volt potential. Neutral wire is a reverse. See, live wire will carry the current, neutral will carry the reverse path of the current. It is a reverse path to the current, and a neutral wire will be at a 0 volt, earth also will be at 0 volt. In exam they might ask question. So name the 2 wires which are at the same potential, earth, neutral and earth. Okay, fine. And from here, see near the pole, children, very see near the what we can say the electric pole will be there. There a company people will arrange a fuse called pole fuse. It is almost it is about 50 amperes rating will be there. Means when current exceeds 50 amperes, it will get fused. Only authorized person only will have that access to repair it. We don't have any access. Okay, fine. From here it will go to the kWh meter. What is the kWh meter specialty? It is a device which measures the electrical energy consumed, and near the kilowatt hour meter only local earthing is done. From here, children, only live wire and neutral wire will pass through the main switch. This is what actually is the main switch. Main switch is a best example for a what? Double pole switch. What is the specialty of this main switch, children? Normal switch, it disconnects only live wire, but whereas main switch disconnects live wire and neutral wire at the same time. From here means through main switch earth wire won't go here. Again these 3 are connected to the MCBs. We will be having MCB board will be there in our houses. So all these 3 wires will go to the MCB board where from there again we will be taking connection to the different rooms. Is it clear? So this is all about actually power transmission and power distribution. And here, children, from here only we will prefer actually here previously we had a tree system, but now we are preferring a ring system. Just I'll try to show the diagram, you can look into that actually. So here what is a, see children, examination point of view, this diagram is very important. So why we are preferring a ring system, children? Many reasons are there. In that 2 main reasons are there. So each and every electric appliance has separate fuse with a separate rating. And even it is cost effective, means it reduces due to the ring system. Okay, the cost is reduced. Okay, now fine. Now how the electric appliances in our house are connected? Should be in series, should be in parallel. So yes, should be in parallel only. What if they are connected in series, children? Yes, if one electric appliance stop working, all other electric appliances also stop working. If one electric appliance gets damaged, you cannot use other electric appliances. But whereas when it comes to the parallel combination, children, yes, each and every electric appliance has its own switch. If one electric appliance stop working also, no problem, other electric appliance will work as usual. Clear? Fine. Now come to the fuse, children. What is the main purpose of fuse? It is like a safety guard, which limits the amount of current which is entering into the circuits so as to save the circuit from overloading and a short circuit. And this fuse wire is made up of the lead and tin. It has high resistance and a low melting point, and it is always connected in live wire, means it is always connected in series with a live wire only. Is it clear? Fine. And in exam they might ask a question, why can't we use copper and aluminum as a fuse wire actually? Yes, if you want you can use, but the problem is that the melting point of aluminum and copper is very high. Though huge current is flowing into the circuit, they don't stop actually, but they have to stop, right? That's what, because of their high melting point only, they are not preferred as a fuse wire. This you have to remember. Comes to the local earthing, children. What is the main purpose of local earthing? Somehow if any electric what we can say appliance gets damaged, means inside, if that live wire will get any damage, it may directly come in contact with the electric appliance. When we are using, we may get electric shock. To overcome that problem only, we need a earthing, means each and every electric appliance must be given a earth connection. And here the very important thing is that here, so this earth wire is always connected to the metallic body or metal case of an electric appliance. In exam they may ask a question, to which part of the electric appliance the earth wire is connected, metallic body or metallic case. Fine, children. Now come to the switch. What is the purpose of switch? To on or off the circuit, or to connect, to disconnect the circuit. Here we have two types of switches, single pole switch, double pole switch. Single pole switches only will disconnect the live wire. Double pole switches will disconnect live wire and neutral wire at the same time. The best example is main switch. Okay, fine. So dual control switch diagrams are very important. So generally we know that, see nowadays it's a quite natural, everybody is having this dual control switch with which we can operate the same electric device from the two different rooms actually. So here is switch 1, here is switch 2. Children, by default either BC or AB are connected, or here AB or BC are connected. Now, can the bulb glow? No, it won't go. Why? Because circuit gets disconnected. If you want to glow this one actually, either you can tap here or here. For example, S2 is some other room, let us say that. If you can tap this, what will happen? This will get disconnected and this will get connected. So that what will happen? Yes, now circuit gets connected, so bulb will glow. So current pass through it. So this is on mode. Try to understand. Either AB should be connected or BC should be connected in on mode. Off mode means diagonally it should get connected. Either AB, BC or AB, BC here. Okay, now fine. Comes to the 3-pin plug, children. This is very, very important here. So diagram might be given. They will ask you to recognize the terminals. Yes, it is the earth pin. Left one is live one. Right one is a neutral one. And two questions can be expected. Why earth wire is long? So that earth connection is made. Earth means earth connection is established first. Why it is a thick? By mistake also it should not be placed in either in a live hole or a neutral hole. And one more thing, why this splitting is given here? So as to have some spring action due to which it is held properly. Okay, now fine. Now socket, children. Yes, here we have to just recognize these terminals. Earth one, neutral one, live. Here see, don't get confused. Here it is a live neutral, but here neutral live. Don't get confused. Come to the color coding. Here we have old convention, new convention. According to the old convention, live is a red color, neutral is what, children? It's a black color, and earth is a green color. But better go for a new convention. With a new convention, live wire is with a brown color we use. Okay, brown color wire. For a neutral is a light blue, and the earth is yellow. And the last topic in this household circuit is what, children? High tension wires. What is the main purpose of high tension wires? To carry the large amounts of current. Then what are the characteristics of the, what we can say, a high tension wire? There are two properties, very, very important. They should have low resistance so that they will carry high currents. Second is a large surface area. Why they should have a large surface area, children? Children, whenever current is passing through the wire, definitely some amount of energy is lost, which is due to which some heat is produced. That heat should escape actually, otherwise the wire might melt actually. So if surface area is large, then what will happen? Heat in the form of radiation will escape easily. Is it clear? So these are the topics in a very shortcut. Okay, na? So topics of a household circuits. Just make a note of it. Yes, now we see the concepts of electromagnetism. In this first, children, Oersted experiment. Actually, what is the main concept? What he proved? He proved that whenever current passes through a conductor, there will be a magnetic field around the current carrying conductor. And by increasing the amount of current, we can increase the strength of the magnetic field around the current carrying conductor. And even by changing the direction of current, we can change the direction of magnetic field around the current carrying conductor. So this only here means how to know that, because magnetic field is, of course, magnetic field is a vector quantity and it is not visible. Then how we will know? Yes, for that only we will take the help of magnetic needle. Look at here. So in the first two cases, current carrying conductor is above the needle. Remember, that's very important. Such that if a current is flowing from south to north, then the north pole of the magnetic needle gets deflected towards west. Snow word you can remember there. In the second case, we reverse the direction of current. Then what happened? North pole of the magnetic needle gets deflected towards east, which means what? Magnetic field is reversed. In the next two cases, current carrying conductor is below the magnetic needle. So in the first case, a current is flowing from south to north only, but as it is above the current carrying conductor, this north pole gets deflected towards east. And whereas in a fourth case, the magnetic needle or north pole of the magnetic needle gets deflected towards the west. Okay, na? So here you can remember snow, S-N-O-W, and here we can remember N-S-E. So nose you can remember, so that you can remember. Okay, it's not a matter how to remember, it's up to you. If you have better clues, you can go ahead. Okay, fine. But the thing is that, so okay, there is a magnetic field around the current carrying conductor. But how to know the direction of magnetic field around the current carrying conductor? Yes, for that only we use right hand thumb rule. So right hand thumb rule will give you the direction of magnetic field. Means right hand thumb rule is used to determine the direction of magnetic field around the current carrying straight conductor. Look at here, means what is right hand thumb rule, children? Just assume that a current carrying conductor is held with your right hand such that thumb should be in the direction of current, so that these four fingers, the direction in which you are curling, will be the direction of magnetic field. In the first case here, so current is flowing vertical upward direction, so the magnetic field will be anti-clockwise. In the second case, current is flowing downward direction, so field lines are clockwise direction. Done? Fine. Now even let us take a coil. If a current is passing through the coil also, children, definitely it behaves like a magnetic dipole. Then how to identify the polarities of the current carrying loop actually? So for that only we are going to use a clock rule, children. So in this coil, if a current is flowing in a clockwise direction, look at here. If a current is flowing in a clockwise direction, then it takes south polarity. Whereas in this current is flowing in anti-clockwise direction, and this phase will take as a north pole. So based on this only, again we can identify the solenoid. We can understand the solenoid and electromagnetic concept. Now come to the solenoid. What is solenoid, children? How it will be? How it seems to be? You know, we might be doing a spiral bending notion. That spiral will be there. Yes, if it is made up of with a copper coil, for that a battery is given, then current will be flowing through that coil. Yes, then it behaves like a solenoid. And children, experimentally it has been proved that current carrying solenoid behaves like a bar magnet. There are two similarities. What is that? So first similarity, children, we know that when a bar magnet is suspended freely, what happens? It comes to the rest by showing geographical north and south. Similarly, current carrying solenoid is suspended freely. It comes to the rest by showing geographical north and south. And second similarity is that, yes, the magnetic field around the current carrying solenoid resembles the magnetic field around the bar magnet. Okay, now fine. Look at here, children. Then how to identify the polarities? For example, here if your switch is on, current is flowing. Here at this end A, children, please try to understand how current is entering like this. In a clockwise direction, current is entering. So this is a south pole. Obviously, your current is entering clockwise direction. Your current has to leave in a anti-clockwise direction only. So obviously, it should take a north pole. Then what are the differences between solenoid and a bar magnet? For a bar magnet, children, can we change the polarity? No, we can't change. But for a solenoid, by changing the terminals of the battery, we can change the polarity. For a given bar magnet, can you change the strength? No. But for a solenoid, we can change the strength of the magnetic field. Here we have three ways to change the strength of the magnetic field around the solenoid. What is that? First one, by increasing the current. Second one, by increasing the number of turns. Third one, by keeping the soft iron core inside of the solenoid along its length. There are the three ways to increase the strength of the magnetic field due to the solenoid. Now comes to the electromagnet, children. So let us see the electromagnet versus permanent magnet. Electromagnet is made up of with a soft iron, whereas permanent magnet is made up of with the steel, children. So here is a diagram, try to understand. So here also children, why we are using soft iron? Because of its retentivity is less, means it gains the magnetic properties immediately, at the same time it loses the magnetic properties immediately. So the moment when you switch on the circuit, yes, current start flowing, yes, here like this. Now look at here. So at this end children, current is flowing in anti-clockwise direction, sorry, clockwise direction. So it's the south pole, here is the north pole. Okay, now fine. And what are the differences between electromagnet and a permanent magnet children here? So for a, sorry, electromagnet, permanent magnet. So for a permanent magnet, polarities can't be changed. For electromagnet, polarities can be changed. For a permanent magnet, we can't increase the strength. For electromagnet, we can increase the strength. Permanent magnet is made up of the steel. Electromagnet is made up of the soft iron. Then how can we increase the strength of the electromagnet? We have two ways. One is by increasing the magnitude of the current. Second one is by increasing the number of turns of the coil. Okay, na? Done. Now comes to the children. We know that when a current passes through a conductor, obviously there will be a magnetic field. Now this current carrying conductor is placed in a magnetic field. What happens? Some force acts on it. How to calculate that force children? Yes, F is equal to BIL. So force acting on a current carrying conductor placed in a magnetic field. Here we have two important conditions. If that current carrying conductor is either parallel or anti-parallel to the magnetic field, then what happens? Minimum force will act, that is 0. But only when current carrying conductor is perpendicular to the magnetic field, then only maximum force will act. How much force? BIL. What is B? Magnetic field strength. What is I? Current. What is L? Length of the conductor. Okay. From this formula, we can derive the, or we can say, units of the magnetic field. So as F is equal to BIL, B is equal to F by L, that is Newton per ampere meter or Weber per meter square or Tesla, and we have even Gauss also. 1 Tesla is equal to 10 power Gauss. Tesla is a SI unit, Gauss is a CGS unit. Now here children, okay, so this is a formula which we use to calculate the amount of force acting on the current carrying conductor placed in a magnetic field. But force is a vector quantity, right? So for that we should know the direction. How to find the direction of force acting on a current carrying conductor placed in a magnetic field? For that we are going to use Fleming's left hand rule. Children, stretch the central finger, forefinger, thumb finger such a way that 3 should be mutually perpendicular to each other. Then children, if C will show that if central finger will be in the direction of current, forefinger will be in the direction of magnetic field, then thumb finger will give you the direction of force acting on the current carrying conductor which has been placed in a magnetic field. Clear? Fine. Now electric motor. What is electric motor? A device which will convert electrical energy to mechanical energy is called what children? Electric motor. Then what is the principle children? The very important thing is that here, when current carrying rectangular copper coil is placed in a uniform magnetic field, it is acted upon by some couple so that it rotates continuously. This is the principle of working of electric motor. Children, what is the net force acting on the current carrying copper coil here? 0. Only here couple will act. As a result of couple, it will be rotated. Examination point of view, this diagram is very important. Here one important thing which we have to notice, this half slip rings C1, C2. These two are called commutators. What is the use of the commutators? They are the rotating devices which are used to change the direction of current for every half cycle or 180 degrees. And here children, rotations per minute of electric motor depends on 4 factors. One is surface area of the coil, magnetic field strength of the bar magnets, the amount of current which is flowing through the conductor, the amount of flowing through the copper coil, and the N is what? The number of turns of the coil. Is that clear? Just make a note of it. Just draw this diagram also. Now we see the electromagnetic induction. Here is output. Yes children. Now comes to the electromagnetic induction. So if you want to understand electromagnetic induction, first we should know what is the magnetic flux. Children, the number of magnetic field lines which are passing through a unit normal area is called magnetic flux. If more number of magnetic field lines are passing, more will be the magnetic flux. If less number of magnetic field lines are passing, less will be the flux. Now actually, see, this is a concept quite opposite to the what actually Oersted experiment, and it is connected by Faraday. So what happened here? Just we will see the main points of the Faraday's experiment actually. So children, whenever there is a relative motion between the coil and a magnet, relative motion means what? For example, coil is at rest, bar magnet is moved, or bar magnet is at rest, coil is moved, or both are moved. So whenever there is a relative motion between the bar magnet and coil, induced EMF is produced, which causes induced current. This phenomena only we can call it as electromagnetic induction. But during this process, what is happening, children? As we are just bringing the magnet towards the coil, taking away from the coil, during this process, there will be a change in the magnetic flux. So whenever there is a change in magnetic flux linked with the coil, there will be a EMF. So whenever there is EMF, there is a current, so called induced current. Clear? Fine, children. So whatever the current which is flowing in the conductor, what in this coil, children, okay, now it can be increased by rapid motion, because as you are making rapid motion, maximum will be the change in magnetic flux linked with the coil, hence current is increased. Second, strong magnets. By using the strong magnets, if you can use a more strong magnet, more will be the number of field lines will be there, more will the number of field lines will be passing through the coil, and more will be the magnetic flux. Third one, increasing the surface area and the number of the coil, hence more will be the magnetic flux linked to the coil. Clear? Fine. Now children, here the important thing is that here Faraday's laws of electromagnetic induction. There we have two Faraday's laws of electromagnetic induction. What is the first one, children? Whenever there is a change in magnetic flux linked with the coil, there will be an induced EMF. First one. Second one, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. More will be the rate of change of magnetic flux, more will be the EMF. Less will be the rate of change of magnetic flux, less will be the EMF. And here the factors affecting the induced EMF, two factors. So means magnet, what is the magnitude of the EMF which is developed or induced depends on two factors. One is what? Rate of change of magnetic flux. And the second one, number of turns of the coil also. So EMF depends on even number of turns of the coil. Clear? Fine. Okay, during this process very clear that current is induced. But how to find the direction of induced current? Here we have two rules actually. One is Lenz rule, second one is Fleming's right hand rule. So both are used to determine the direction of induced current only. But small difference is there. Lenz law is used to determine the direction of induced current in the coil, and it is based on law of conservation of energy. And the Fleming's right hand rule is used to determine the direction of induced current in the linear conductors. Children, when you can notice a mathematical form of the Faraday's second law of electromagnetic induction here, induced EMF or induced current is equal to minus N into d pi by dt. This minus represents actually regarding this minus only, explanation is given by Lenz law. What does it state, children? It states that direction of induced means the induced current takes a direction such a way that it opposes the cause which produces it. Clear? Fine. Now what is a Fleming's right hand rule? Yes, stretch the central finger, forefinger, thumb finger such a that three should be mutually perpendicular to each other. Then if forefinger shows the direction of field, thumb shows the direction of what we can say motion of the conductor, then central finger gives the direction of induced current. Clear? Fine. Now children, comes to the AC generator. So in AC generator what will happen? Mechanical energy is converted into electrical energy. And the diagram setup, children, it is almost similar to the DC generator only, but the difference is that for a DC generator half slip rings will be there, and here what, children, here complete slip ring will be there. Here braces B1 and here is B2. Their battery will be there. Here load resistance is what plays so as to utilize the whatever the electrical energy so produced. Okay, now fine. And children, what are the differences between DC motor and AC generator? Difference I am talking. DC motor converts electrical energy into mechanical energy. AC generator, mechanical energy into electrical energy. DC motor, in that half slip rings will be there. In AC generator, complete slip rings will be there. What are the similarities? Yes, in both devices, what happens? The energy conversion takes place. Yes, and the second one, in both cases, coil will be rotating. These are the similarities. Okay, na? Done. So it is about a AC generator, and it is a what we can say is a EMF, and E naught is a maximum value of EMF, children. So the maximum value of EMF. So it depends. How can we increase the maximum value of EMF so that we should have a maximum current, children? Yes, by these three factors. By increasing the number of turns of the coil, by increasing the surface area of the coil, by increasing the speed of rotation of coil, we can increase the EMF value. so that current can be increased. And here one important thing is that children, here the frequency of the AC current generated depends on the number of rotations of the coil. More the number of rotations, more the number of, what more is the frequency. Exactly, this is very important. So frequency of the current generated depends on the number of rotations of the coil. Okay, now fine. So now comes the transformer, children. So first of all, on which principle does it work? Transformer works on electromagnetic induction. It only will alter, it only will change the input EMF or input voltage. Okay, now fine. Now, and one more thing is that it cannot change the frequency. It won't change, it only will change the voltage, children. It only will change the voltage, and it works with only AC but not DC current. So here we have two types of transformers, step up transformer, step down transformer. Here two coils will be there, one soft iron core, two coils. What is the primary coil? What is the secondary coil? So the coil across which input is given is the primary coil. The coil across which we obtain output is a secondary coil. Okay, now. Fine, children. In a step up transformer, number of turns are more in a secondary coil than for primary coil. And one more thing, in a step up transformer, very important, primary thickness of the primary coil is more. Why? Thickness is more means current is more. Current is more means EMF is less. Here EMF is less, here EMF is more. Step up, EMF is increased. And where is in a step down transformer, children? Secondary number of turns in the secondary coil is less. And the very important thing is that here, yes, the thickness of the secondary coil is more in a step down transformer. Why? More is the thickness, it carries more current. More the current, less is the EMF. So here more EMF, less EMF. EMF is step down, it is a decreased. So applications means what? Transformers are used in electric bells, in some electric gadgets. Even during the power transmission also we use, right, step up transformers, step down transformers. So these are the concepts of what, children? Electromagnetism. Just copy it. Now children, we will discuss the calorimetric concepts. Okay, fine. Look at here. So first, heat, children. Here, what is a heat? Heat is a form of energy which always flows from a body of high temperature to body of low temperature. Its SI units are joules, CGS units are calories. 1 calorie is equal to 4.2 joules and 1 joule is equal to 0.24 calories. Fine? Yes. Next, temperature. What is the temperature, children? The degree of hotness or coldness of a substance is called temperature. But even temperature can be defined in terms of kinetic energy. How, children? The temperature is nothing but the average kinetic energy of the molecules of a substance. Means very important. So here very important things are here. So here kinetic energy of the molecules will decide the temperature. Children, this point is very important when we are learning the state of change, because during the change of state, as temperature remains constant, the kinetic energy of the molecules also remains constant. Only during the change of state, potential energy will change. That's fine. Okay, children. Next, here one important thing is that here the SI units of temperature are Kelvin, CGS are degree Celsius. But the conversions are very important. When you convert degree Celsius to Kelvin, children, you should add 273. Whereas if you want to convert Kelvin to degree Celsius, you have to do the minus 273. Is it clear? Fine, children, here. But the very important thing is that, okay, this is a change in, what we can say, this is all about the temperatures. But when it comes to the change in temperature, I mean, when we are talking about a rise in temperature or a fall in temperature, here we need to remember one important thing. What is that here? The rise, either the rise in temperature or a fall in temperature is same in a Kelvin scale as well as degrees, what we can say, Celsius scale also. Which means what here? 1 degree Celsius rise in temperature or fall in temperature is equal to the 1 Kelvin rise in temperature or fall in temperature. And here the heat. So children, so whenever you can give a heat to a substance, children, I mean, so heat is absorbed, and even it's a reverse process also can happen, that is heat is liberated. But either heat absorption or liberate, what we can say, rejection, depends on few factors. So either the heat absorbed or rejected, children, it depends on the nature of the material, mass of the substance and change in temperature. So the amount of heat needed is directly proportional to the mass and even directly proportional to the change in temperature. So here you get this formula, Q is equal to mc delta t. It's a very important when we are solving the numerical. So at the end of this calorimetry chapter, I'll tell you the importance of this formula, Q is equal to mc delta t. Now let us see what is heat capacity or thermal capacity. Children, let us take some amount of mass. Let us take a substance. Let us take some substance. If you want to raise the temperature of that particular substance by 1 degree Celsius, then some amount of heat is required. That amount of heat only we can call it as a heat capacity or thermal capacity. I repeat once again. The amount of heat energy required to raise the temperature of whole body by 1 degree Celsius is called heat capacity or thermal capacity. So this heat capacity or thermal capacity depends on two factors. That is, it depends on mass, it depends on nature of the substance or nature of the material. So mathematically it can be expressed C dash is equal to Q by delta T. Its SI units are joule per Kelvin, CJ units are calorie per degree Celsius. Examination point of view, applications are very important. Children, here we need to remember one important point. If more is a mass, more is the thermal capacity. Less is a mass, less is the thermal capacity. First, let us try to feel the concept of thermal capacity. Thermal capacity or heat capacity means what? The ability to retain the heat in it for a long time. So if it has a more mass, it it retains heat in it more time actually. If less is mass means it does not keep any heat in it actually. Okay, fine. So based on this only we have applications. Children, if you can notice here, electric iron, the base of the electric iron is made with what we can say very thick material. Even cooking pans also provide with a very thick base. What is the reason? Children, so thickness is more. Thickness is more means what here? Mass is more. Mass is more means specific, what we can say heat capacity or thermal capacity is more. So that what will happen? For a long time heat is remain. So for electric iron, if it has a thick base, for a long time it can carry the heat. So that you can do, though you can switch off the current, what will happen? For a long time you can do the electric current. Long time is not months and years. Okay, compare with the electric current with the thin base I am talking. And here why cooking pans, as I told you that they have a thick base, so that more mass, more thermal capacity. So that what will happen, they will retain heat in it for a long time. That's why though you can cook the foods mornings, for a long time the food items will be warm. Okay, fine. Whereas it comes to the calorimeter. Calorimeter is made up of the thin copper vessel. Okay, why copper we will discuss later. But why thin? So thin means what, children? Less mass. Less mass means less heat capacity. So that calorimeter does not retain heat in it. Whatever the heat is given to the calorimeter, it is given to the ingredients. Okay, this is all about heat capacity or thermal capacity. Now, next come to the specific heat capacity. This will represent with the letter C. Thermal capacity C dash. So, what is the specific heat capacity, children? Let us take a unit mass. For suppose it is at a 5 degrees Celsius. We want to raise its temperature to 6 degrees Celsius, which means what? Change in temperature is how much? 1 degree Celsius. For this, whatever the amount of heat is required is called specific heat capacity, which means what here? The amount of heat energy required to raise the temperature of unit mass of a substance by 1 degree Celsius is called specific heat capacity. Specific heat capacity does not depend on the mass. It depends only on the nature of the material. So it is a characteristic property of the nature. What you can say, it's a material. So mathematically, as we know that here Q is equal to mc delta T. Here C is called what? Specific heat capacity. Let us make C as a subject. Then you will get C is equal to Q by m delta T. M delta T. So its SI units are joule per kg Kelvin. CJ units are calorie per gram degree Celsius. As I told you that it depends only on the nature of the material but not on the mass. And children, so of all known substances, water has highest specific heat capacity, that is 1 calorie per gram degree Celsius, or you also can express in terms of SI units, that is 4200 joule per kg Kelvin. So because of high specific heat capacity of water, we will find many applications. So because of this reason only, water is used as a coolant, water is used as a heat reservoir, water is, farmers during the night times, they will fill their fields with the water. Because of what? High specific heat capacity. And even we know that land breeze and sea breeze can occur just because of high specific heat capacity of water. Is it clear? Fine. Now come to the calorimeter, children. What is a calorimeter? A thin copper vessel, a cylindrical thin copper vessel is called calorimeter. Here two questions will be there. Why only thin means already discussed, so that it should have a low thermal capacity, so that whatever the heat is given to the calorimeter must be given to the ingredients. But why it should be made up of with the copper only? Because its specific heat capacity is less. Children, always will choose the material to make the calorimeter with a low specific heat capacity, so that it acts as a best conductor. Low specific capacity, best conductor. High specific capacity, best, what we can say, insulator, I can say that. Okay, na? Fine, children. Now, so here, so whenever we are using calorimeter, what is the purpose of calorimeter? Either we can measure heat loss or heat gain. So whenever we are measuring this heat, children, definitely there will be some heat loss. So heat loss can happen in three processes. What is that? Conduction, convection, radiation. But how can we overcome the heat loss? So try to understand, children. The calorimeter is placed in a wooden box, and the gaps between the calorimeter and wooden box filled with some insulating material such as a cotton, wool. Okay, na? So as to reduce the heat loss to the conduction. Then how can we minimize the heat loss to the convection? That calorimeter is closed with a wooden lid, so as to minimize the heat loss to the convection. And whereas the inner surface of the calorimeter is polished, highly polished, so that what will happen, the amount of heat whatever is about to lose in the form of radiation is trapped inside only. Okay, now fine, children. Now principle of calorimeter, it is also called as principle of method of mixture. It is based on law of conservation of energy. So according to principle of calorimeter, children, whenever you can mix hot body with a cold body, obviously hot body will lose heat, cold body gain heat. So according to this, the amount of heat lost by the hot body is always equal to the amount of heat gained by the cold body, provided there is no heat loss to the surroundings. For suppose, children, here, so hot body of mass m1, specific capacity c1, temperature t1, another body, cold body of mass m2, sorry, it is m2, specific capacity c2, temperature t2. If both are mixed, then definitely what will happen, there will be a heat exchange. Hot body will be losing heat, cold body will be gaining heat. After some time, both will be in what we call thermal equilibrium. So in thermal equilibrium, T will be the resultant temperature. Here you should understand about delta T1, delta T2. Delta T1, fall in temperature of hot body. Delta T2, what we can say, rise in temperature of cold body. So according to this, anyhow, heat is equal to mc delta T. As per this, we have written heat loss by the hot body is equal to heat gained by the cold body. So delta T1 can be expressed T minus T1, delta T2 can be expressed T minus T2. If you can simplify this, children, you will get T is equal to M1 C1 T1 plus M2 C2 T2 by M1 C1 plus M2 C2. But what if both bodies have same nature? I mean, hot water is mixed with the cold water. As nature is same, specific heat capacity is same. So which means what? C1 will be equal to C2. In that case, how to find the resultant temperature? This formula, T is equal to M1 T1 plus M2 C2 by M1 plus M2. Children, here one important relation which we forgot. What is that? The relation between specific heat capacity and thermal heat capacity. So here we know that here C is equal to Q by M delta T. So let me use this space. Okay, now fine. So we know that here C is equal to Q by M delta T. But this Q by delta T is nothing but what actually is a C dash. So it can be written as C is equal to C dash by M. So finally C dash is equal to M into C. So thermal capacity is equal to mass into specific heat capacity. Is it clear? Just copy it, children. Cold. Okay, children. So we all know very well that matter can exist in three states: solids, liquids, gases. But here, by giving heat or by taking out heat from that particular substance, we can change matter from one state to another state. That only we can call it a change of state or change of phase. Is it clear? Fine, children. Now look at here. So what is this process called? The conversion from solid state to liquid state, we can call it as a melting. Whereas the liquid state to gas state we can call it as a boiling. In these two processes will happen on heating. On cooling, again what will happen? Gas will convert into liquid. This only we can call it as it's a what we can call as a liquefaction. The process of conversion from gaseous state to liquid state is called liquefaction, whereas the process of conversion from liquid state to solid state is called freezing. But the very important point which we notice that during this process, temperature remains constant. During the change of state, temperature remains constant. And it is also possible that solid can directly convert into gaseous state. This is called sublimation, and this reverse process is called deposition, that is gaseous state to solid state. Clear? Fine children. Now what is a melting point? The standard temperature or the constant temperature at which solid changes into liquid is called melting point. So at what temperature ice melts, children? 0 degrees Celsius. So the melting point of ice depends on two factors. One is the pressure, another one is impurities, children. So if you increase the pressure, melting point of ice decreases. With the addition of impurities, melting point decreases. Means with both, with the pressure, with the impurities, melting point of ice decreases. What is a boiling point, children? The constant temperature at which liquid changes into gas is called boiling point. So what is the boiling point of pure water? Pure water is 100 degrees Celsius. And here what are the factors which affects the boiling point, children? Here two factors, pressure and impurities. But here thing is that with the pressure, boiling point means by increasing the pressure, boiling point increases. That is the reason inside of the pressure cooker, water boils at around 120 to 125 degrees Celsius because pressure will be more. And here with the addition of impurities also, boiling point of water increases. Example, sea water, because it has some impurities and salts. So it what we can say boils around at 115 degrees Celsius. Clear? Fine children. And one more thing is in that here, children. So whenever you can take ice, just try to put in a vessel which is placed in a stove, some fire, we are giving the heat. Do you think that total ice will melt at the same time? No. Slowly it will start melting. Means initially let us say that the temperature of the ice is 0 degrees Celsius. When it start melting, so there will be mixture of ice and water will be there. In this what we can stage also, the temperature will be 0 degrees Celsius. This is constant. This temperature will remain constant till whole ice melts. Which means what? During the change of state, temperature remains constant. But for these children, so means to change the state of a substance, to change the what we can state of a particular substance from one form to another form, we need to provide heat, right? This amount of heat only we can call it as a latent heat, specific latent heat. Why we are saying it is actually specific latent heat? If it is a 1 unit mass, if you can take a unit mass, the amount of heat required we can call it the specific latent heat. So the amount of heat energy what we can say required to change the unit mass of a substance from one state to another state at a constant temperature is called specific latent heat. So mathematically it is L is equal to specific latent heat, it is L is equal to Q by M. Its SI units are joule per kg, CG units are calorie per gram. So this L is equal to Q by M only, we can rewrite like a Q is equal to ml. So there is importance with this also. Now children, specific latent heat, what we specific latent heat of fusion of ice is 80 calorie per gram or 336 joule per gram. What does it mean? It means that children, for suppose here, ice at 0 degrees Celsius, in order to melt, to convert into water at 0 degrees Celsius, means 1 gram of ice at 0 degrees Celsius to convert into 1 gram of water at 0 degrees Celsius. How much amount of heat is required? 80 calorie heat is required. Means to melt 1 gram of ice, children, how much amount of heat is needed? 80 calories. If you want to express in terms of joule, 336 joule. In order to melt ice at 0 degrees Celsius, how much amount of heat is needed? 336 joules. And here we have applications of high specific latent heat of fusion of ice. For suppose children, so whenever we want to have a juice, if it's a hot summer, definitely we will prefer a, it's a cool one. Do you prefer juice with a high temperature, low temperature? Low temperature only. But that juice can be cooled with the two methods, by adding ice cubes, by adding a water. But do we prefer water? No. Why? The reason is that ice has a specific what we can say latent heat of specific latent heat of fusion, that is 80 calorie per gram. The moment when ice is added into the juice, in a 1 gram of ice to melt, it takes a 80 calorie heat. From where it will take? From juice it will take. So which means what here? Juice is losing the heat, so it will become very cold easily. That's what we can prefer this combination, juice plus with ice only, but not with the water, means ice cold water only, but still we don't prefer. Even whenever we are, for example, when we are eating ice cream, sometimes some children will crush the ice. What will happen? They'll get some soothing kind of pain, right? What is the reason? The moment when you crush ice, it will melt. But to melt, 1 gram of ice takes 80 calories. From where it will take? From our body only it will take. Is it clear? Fine. And even after hailstorm, surroundings will become very cool. Even when frozen lake is melting also, the surroundings will become very, very cold. The reason is that, children, as we know that to melt 1 gram of ice at a 0 degree Celsius, 80 calories what heat is needed. But in this process, during these two situations, ice has to be melted. For that, heat is required. From where the heat is absorbed? From the surroundings. From the surroundings only, the ice will absorb the heat. So that surroundings will be losing the heat. So that what will happen? Surrounding temperature will fall. So that it will become very chilled. Okay, fine. So children, when it comes to the numericals, so anyhow we are not going to discuss the numericals. Okay now. So here, children, if you need a numericals and in detail explanation, everything I will give in a description. Links will be given. Just go through that. So here two formulas we will get in this calorimetry. Q is equal to mc delta T and Q is equal to ml. So when we should use this formula? When we should use this formula is very important. So these both formulas are used to calculate the amount of heat required only. But difference is that this first formula is used to calculate the amount of heat when there is a change in temperature. Whereas this second formula Q is equal to ml is used to calculate the amount of heat energy required only. But when there is no change in temperature, rather when there is a change in state. Is it clear? So these are the concepts. These are the concept calorimetry. Just copy it. Now we discuss the concept of radioactivity. Yes, children, we have come to the almost conclusion. Yes, that is the last chapter which we will be discussing now. I mean, we are revising. That is radioactivity. Chalo. So children, it is a scoring chapter. Some students, they have a problems with the numerical, then those students can target this chapter so that you can score the best marks in this chapter. Okay, now come on. So structure of an atom, children. So if you can just see the atom, children, here. So protons and neutrons together called nucleons. They will be residing in a small region, so called nucleus. Around the nucleus, electrons will be revolving around around the nucleus in a particular cells or orbits, so called stationary shells or stationary orbits. Clear? Fine. What is the atomic number, children? So the number of protons in an atom is called atomic number. In a neutral atom, number of protons are equal to the number of electrons. And what is the mass number, children, here? The number of the nucleons, that is number of neutrons plus number of protons, is called mass number. That is A is equal to Z plus N. If you want to find the number of neutrons, N is equal to A minus Z. Clear? Fine. Now see the types of nuclei. First one, isotopes, children. So the atoms belongs to the same element having same atomic number but different mass number are called isotopes. Here we have a stable isotopes and unstable isotopes. In the stable isotopes, the number of protons are equal to the number of neutrons. And unstable isotopes, number of neutrons are more than the number of protons, which are radioactive in nature. Comes to the isobars, children. So the atoms with a different atomic number but same mass number are called isobars. And here we need to recall about the mirror isobars. What are mirror isobars? The isobars in which number of protons and neutrons are interchanged. Okay, na? Fine. Now come to the isotones, children. So the atoms with a different atomic number, different mass number, but same neutron number. Here 31 minus 14, 32 minus 15 is the number of neutrons 17. Such a nucleus are called actually isotones. Clear? Fine. Comes to the radioactivity, children. It is not a plan. It is an accidental discovery by Henry Becquerel actually. So he could notice that kind of rays are coming from the materials like uranium, and he named those rays as a Becquerel rays only. But later it was proved that yes, the material so-called radioactive substances like uranium, they are emitting the radiations consisting of alpha, beta, gamma. Okay, na, so as to get the stability. It's a very important. Okay, na, fine. So this phenomena only we can call the radioactivity. So radioactivity is what actually is a random process it is, and it is a nuclear phenomena. Why it is a nuclear phenomena? First, why it is a nuclear phenomena? First, we need to understand one more important point. If it was due to the electrons, then there would be impact of pressure, there would be impact of temperature, there would be impact of oxidation reduction. But if you can change all these things, then amount of radiation which is emitted won't change, which means what are the radiations which are emitted is not due to the orbital electrons, it is due to the nucleons. Hence radioactivity is a nuclear phenomenon. Now children, what are the radiation which is emitted? Okay, first here look at here. So here a little bit amount of radioactive substance taken in a lead cavity. Here it is. Why only lead? Because lead is a more stable one. Why here only narrow slit is made? So that to get a beam of radiation. When this beam of radiation pass through electric field, children, it is noticed that it is getting split into three regions. Some kind of radiations are going towards the negative, some kind of radiations are going towards the positive, some radiations are going undeviated. So which means what here? Some radiations are positively charged, some radiations are negatively charged, some radiations are what we can say neutral. So later it was proved that so alpha will go towards the negative charge, beta will go towards the positive charge. Okay, and one more thing we have to notice, beta will deviate more than that of alpha. Why? Because beta are lighter than that of the alpha. Okay, na? Fine. Now we see the alpha particles properties actually. So alpha particle is nothing but the doubly ionized helium. Okay, na? Fine. So these alpha particles, and the symbol is He24, and these are positively charged one, children. The charge of the alpha particle is double the charge of the proton. The mass of the alpha particle is 4 times of the mass of the proton. Okay, fine. And these alpha particles will have high ionizing power, low penetration, and the velocity is in the order of 10 power 7 meter per second. And these alpha particles will affect the photographic plates. Okay, na? Fine, children. Now come to the beta particles. Beta particles are nothing but the fast moving electrons, which means what they are negatively charged one. Children, alpha particles as they are positively charged one, they will get deviated towards the negative terminal electric field. But whereas here beta particles as they are negatively charged one, they will get deviated towards the positive terminal. They will get deviated towards the positive terminal, and their fast moving electron. The speed of the beta particle is 10 power 8 meter per second, and the ionizing powers and penetration powers are in between alpha and beta. When it comes to the ionizing powers, less than beta but more than gamma. When it comes to the penetrating powers, children, more than alpha but less than beta. Okay, now fine. Now comes to the here gamma rays. So gamma rays belongs to the electromagnetic waves, right? So that what will happen, these will travel with the speed of the light in a vacuum, that is 3 into 10 power 8 meter per second, and they are electrically neutral, so they don't get deviated either in electric field or magnetic fields. And the speed is 3 to 10 power 8. And the very important thing is, children, they are high penetrating. That's what they cause a severe biological damage, gamma rays, due to their high penetrating power and least ionization powers. Is that clear? Fine. Come to the alpha decay, beta decay, gamma decay, which means what? From a particular nucleus, if alpha particle is emitted, what will happen? How the atomic number, mass number will get affected? That we have to see that. Okay, fine. So children, if alpha particle is emitted, atomic number of that particular nucleus is decreased by 2 and the mass number is decreased by 4, which means what? If alpha particle is emitted in a periodic table, that particular element, the new element will go 2 steps left side, will move 2 units left side. Example, so uranium 92 238, from this alpha particle is emitted, so here atomic number is decreased by 2, mass number is decreased by 4. And it is a parent nuclei, here is a daughter nuclei. Comes the beta decay. So during the beta decay, children, atomic number is increased by 1, but there is no change in mass number, which means what? After emission of beta particle, the daughter nuclei will move right side in a periodic table, right side 1 step, 1 unit right side. So during a beta decay, what will happen, children? Atomic number is increased by 1. That's what here C614 beta particle is emitted. Yes, atomic number is increased by 1. So it is 7. 7 is with a neutron, nitrogen. But comes to the gamma decay children. So gamma does not carry any charge or any mass. So during the gamma decay, there won't be any change either in atomic number or a mass number. Only there will be change in the energy of the nucleus, because gamma rays are nothing but what children? It's a purely it's a energy. That's it. Okay, fine. Come to the radioisotopes. What are radioisotopes children? So some isotopes of an atoms whose atomic number is less than 82, they are found to be in radioactive nature. Example, cobalt 60, carbon 14, potassium 40. And we have plenty of applications, many applications in different fields which we have. Some important applications are, yes, radioisotopes are used in radiotherapy to cure the cancer, because cobalt 60 is a powerful gamma source of gamma radiation. It is used to cure cancer, so called radiotherapy. And here radiosodium, radioiron, radioiodine, these three are called tracers which are used to find the tumors in the brain and the clots in the blood. And these radioisotopes also, especially carbon 14, is used in a carbon dating. Is it clear? Just copy it. Now we will be discussing the source of harmful radiation and the remaining concepts. Mega electron volt. Yes children, now comes to the sources of harmful radiation. Here we have three sources of harmful radiation. Radioactive fall, which means what? Whenever there something goes wrong in a nuclear reactor, there will be a blast, right? So with that also, the radioactive material may come out. So with which what will happen? All radiations will be coming out actually. So it acts like a source only. Second one, nuclear waste. So children, generally we use like, it's a radioactive material like a uranium. They are used in nuclear reactor. After some days, what will happen? Their radioactivity, means the amount of radiation which they will emit will get decreased. So those kind of things they'll keep aside actually. Those are called as a nuclear waste. But still they have a ability to emit some amount of radiations. Third one is cosmic radiation and X-rays. Okay, fine. Next, harmful effects of radiation. Children, here we have short term. Short term which means what actually? A person who gets exposed to these radiations, after some days he may get cured. And means recoverable. Second one, long term but irrecoverable, means till the person's death he will be suffering only. It's too dangerous. Third one, genetic effects. Not only that particular person, so that will be carried to the future generation, means genetic modification will happen, so that is carried to the future generations. And the safety precautions while using a nuclear energy, means from the beginning of the establishment of the nuclear reactor and the safety till safety disposal, we have to take a lot of care children here. The first one, establishment of the nuclear power plant. So when you are establishing it, make sure it should be established far from the populated area. And around that nuclear reactor core, there must be very thick concrete wall, thick concrete and a lead wall, so that radiations may not come out. And there must be a backup cooling system. Okay, now fine. And the second one, safety measures while handling, means the persons will be working in a nuclear reactor means in that area, right? Nuclear complex and everything. So then what will happen? That particular persons, they must be provided with a lead-lined aprons. They must be given a lead gloves, but still they should not touch with a hand actually. Though lead gloves are there, they have to use long lead tongs should be used. Okay, fine. Third one, safety disposal of nuclear waste. So for this safety disposal children, so that should be taken to the far from the populated area. There it should be buried by keeping in a lead casket. Why only lead children? So that radiations may not come out. Still it is danger only, but still we don't have option. Okay, now fine children. Now come to the background radiation. What are the background radiations? The radiations to which we all are exposed, even though radioactive material is not seen. Such radiations are called background radiations. And one more thing children, we cannot keep ourselves away from the these radiations, because inside our body itself is a radioactive things are there. What is that here? So your background radiation two types. Internal radiation, this is what I am talking. Potassium 40, carbon 14. And external background radiation, radon 222 and even solar radiations comes under external thing. Okay, fine. And it comes to the nuclear energy children. So during nuclear reactions, some amount of mass disappears. That amount of mass will convert into energy. So produce. So during the nuclear reactions, whatever the energy so produced is called nuclear energy. That can be calculated by using E is equal to delta m c square. Here delta m is the mass defect, c is the speed of the light. That is c is equal to 3 into 10 power 8 meter per second. If 1 AMU mass disappears children, 931.5 mega electron volt energy is released. But even 1 kg amount of mass disappears. 9 into 10 power 16 joules or 2.5 into 10 power 10 kilowatt hour energy is released. Okay, now fine. Now comes to the types of nuclear reactions. Their first one is nuclear fission. Fission means what? Actually splitting. Means a heavy nucleus, when it is bombarded with a slow neutron, it gets splitted into almost two half equal nuclei, and in which huge amount of energy is released. Is called nuclear fission. Almost 190 mega electron volt energy released. Here example children, here uranium 92 235 captured one neutron, so got splitted into barium, krypton, 3 neutrons are released. Here you have to check this. Means in a nuclear reactions children, atomic number, mass number is conserved. Means left side and the right side, the atomic number, mass number must be conserved. It is not compulsory that always barium and kryptons are formed. Even lanthanum and bromine also formed. Okay, na? Fine. And children, here in a nuclear fission, whatever 3 neutrons are released, again they will undergo fission reaction. Means it is continued like a chain reactions. Kanaya, Hindi. Mallarappo. Padu. Akade petara. Bujay. అయిపోయింది రుడే రుడా కానీ వాడు ఫీల్ అవుతారు మళ్ళీ. దాదా మమ్మ హాఫ్ అన్ చాలా అయిపోయింది. మా 3 అయిందానే, 3 అయిందా? లాస్ట్ అయిపోతుంది అమ్మా, మరి అయిపోవచ్చు. సరే సరే ఓకే, క్లోజ్. So children, in this nuclear fission reaction, whatever the neutrons which are released, again they will undergo reaction, and again each nuclear fission reaction 3 neutrons are released. It will go like a chain, and which is not in the control. Such a nuclear reaction we can call it uncontrolled chain reaction. That is for a destructive purpose, where we can make a nuclear bomb based on that. But children, for constructive purpose also it can be used. How? Out of these 3 neutrons, if 2 neutrons are controlled, then only a little amount of energy is released, which can be used for a constructive purpose. For what we can use? Yes, in a nuclear reactors we can use. Fine. Now comes to the nuclear fusion reaction children. What is the nuclear fusion? So in this process, a smaller nuclei will get combined to form a huge nuclei. But children, these nuclear fusion reactions can take place only in the sun and the stars. So much of temperature is needed. So almost for this nuclear fusion to happen, 10 power 7 Kelvin amount of temperature is needed. That's what these nuclear fusion reactions are also called thermonuclear reactions. So this what actually look at here, 4 hydrogens are fused so that 1 helium, 2 positrons, okay, 2 neutrinos, and 26.7 mega electron volt energy released. And here one important point thing is that children, if you can calculate the amount of energy per nucleus, if you can calculate, that will be more. I am talking about the energy release per nucleon. Here how many nucleons here? 236 nucleons here, but here only 4 nucleons, right? Try to understand. So the amount of energy per nucleon release will be more in a nuclear fusion reaction than that of the nuclear fission. Is it clear? Yes children, successfully we completed today's Maha marathon. Okay na? Thank you so much for all your support. Okay children, yes, because of you only, yes, because of you all, because of our lovely students, today we are able to just start, and we are able to complete this session children. Yes children, again I am telling you, this is very useful to you all for your revision purpose. Means already you might have prepared a chapters, but just I can say just 24 hours. Tomorrow is the exam. 100% it is useful, because just before the exam it is not possible to cover all chapters, right, if you go through textbook. So we made almost maximum points we could try to cover, except the numericals. And children, the class 10th, all links of all the chapters and numericals all will be given in the description. So if it is needed, just go through that actually, so that you will have, if you want numericals, yes, go through the links which will be given for each and every chapter. All links will try to give here. Is that clear, children? So children, so almost just not almost, just we complete the session. Only one thing I would like to say, that be confident. Yes, thoroughly you prepared. See, you have been preparing since 1 year. Don't get confused, don't get tensed, don't think that whether I can do it or not. Yes, you people can do it, have that confidence. But in exam, children, remember one important thing: if paper is easy, don't be excited. If paper is tough, don't get tensed. Read the question at least once or twice. It's not like just reading the question, writing the answer. Don't come to the conclusion immediately. Sometimes what will happen, you may understand the question if you read twice or thrice only. This is very, very, very important. And the last 10 minutes, children, kindly check the question, what we can say, answer script properly, whether all question numbers are given properly or not. Especially check the units. When you are doing the numericals, children, that units are correct or not. Diagrams, check the labeling. Okay, na? So only one thing, one thing I want to say, that is what? All the very best. Thank you so much. Have a great time to all.